Okay. And we'll go from current slide. Now, before we get started on, on this, let's review where we are, where we're heading, how we're going to get there. Okay? Today is not the last day of class, because this is a mini-term class. We have class on Tuesday as well as today. Okay? Our final exam is scheduled for Thursday. Actually, they put it on the schedule for the following Monday. Okay? Which to me is kind of nuts, because they put all the mini-term classes on one day, even if it's a day you weren't taking that class. So that means you could have two finals on top of each other at the same time, which doesn't make any sense to me. So I'm going to give the final Thursday, okay? Now, hold that in your thoughts, and let's back up a little from there. First thing I want to ask you is, have you done student course evaluations? No, not yet. You have. Good. Not yet. Okay, please do those. You can wait until you see your final grade, that's fine, or the final exam, I don't care, but just don't forget to do it. I can remember when I was an undergraduate, it was a long time ago, but I can remember, boy, when I took that last test, I was so ready to get out of there, I didn't think about, oh, I still need to do that, don't I? Okay.
That's a grade too, if you do the student evaluation.
Yeah.
Survey, that's a grade.
What's that?
That's a grade if you do the student evaluation in this class.
What about it?
You'll get a grade.
Oh, do you get a grade?
Yes.
No, the evaluation is not physical science.
Okay.
So, yeah. But please do it. I mean, I don't believe in bribing students to do something. Okay?
Yeah, I was just saying.
Yeah. To me, that would then be giving you an unbiased thing. I want you to do what it's asking without any pressure from me one way or another, okay? So, please do them, okay? Now, where we are today, we're in Chapter 8. It's the one and only chapter we'll get to do on chemistry, okay? We just barely got started in Chapter 8 on Tuesday. So we got most of the chapter left. However, we did finish Chapter 6 on Tuesday. And we finished the last lab on Chapter 6 on Tuesday. So here's what we've got left to do. Chapter 8, the rest of Chapter 8. And we've got a lab for Chapter 8. We have a test for we have the test for Chapter 6. That will be the last 30 minutes today. The test for Chapter 6 is the last 30 minutes today. Which means if you don't have your formula and equation sheet ready for Chapter 6, that might not be a bad idea to be working on that. Okay? But that said, what we got to do is finish Chapter 8, or at least make good progress on it today. There's no lab today, so the last 30 minutes today will be the test on Chapter 6. That means we got basically not 4 hours now, but close to 4 hours. What's that?
Is our last lab right here?
That's the last lab on Chapter 6. We will have a lab on Chapter 8. Now, it's a paper lab. Okay, it's not anything that we're going to be doing or doing. You're just going to be using the book and getting the answers from the book and from your notes and stuff. Okay? Okay. Probably on Tuesday. Okay. So, here's the deal. Going to get as far as we can in Chapter 8 today. We've got almost 4 hours. Okay, not quite that now, but close to it. We may even finish Chapter 8 today. No problem if we don't, but if we do finish it today, that's one possibility. The last 30 minutes will be your test on Chapter 6, and then that means Tuesday, we're either going to finish Chapter 8 if we didn't finish it today, but definitely have the lab for Chapter 8, because I don't think we'll get to that today. Okay, Demetrius is here. I knew he was here. And I can't find you. There you are. And now he's going to leave again. Okay. So, yeah, we get to see him every now and then. That's it. Okay. All right. All right. So that means Tuesday Either we finish chapter 8 and then do its lab, or if we finish chapter 8 today, then all we've got to do on Tuesday, is the lab for chapter 8. Okay. Now, either way there, we're going to have some time left over on Tuesday. If y'all feel confident and ready to do it, you can take your chapter 8 test Tuesday if you feel like it. I don't like to give a test the same day that we finish a chapter. I like to give you some time to digest it. But if we finish chapter 8 today, then we'll do the lab on chapter 8 on Tuesday plus the test. If we don't finish chapter 8 today, we'll just do the lab, and then if you opt to we'll finish chapter 8 on Tuesday and then do the lab. And then if you opt to do the test on 8, you can. You don't have to. That's not in my cards, but you can put it in yours. Well, here's the other issue then. If we do finish soon enough on Tuesday, if you want to, in addition to doing the test on chapter 8, also do your final exam, that's up to you. So we'll see how things are going at the end of class today, how far we got and that type of thing. And if indeed we're far enough along and you think you're going to want to do everything, you can always change your mind. Well, let me know. Now, here's the reason that there's any question at all. I do want to do pizza for you one day. I was going to do it Thursday, but if enough of you are going to say, no, I'm going to go and try to finish everything on Tuesday, then we'll go on and have pizza on Tuesday.
I'm just trying to finish the lab 8 and the chapter test on 8 on Tuesday and take my exam on Thursday.
On Thursday, okay. If most people are going to do that, we'll have the pizza on Thursday then, okay? Let's plan to do that, okay? So probably Tuesday and Thursday of next week are going to be short days because we only have finishing chapter 8, lab on chapter 8, test on chapter 8, and test on final exam. That's all there is. There's no more chapters to do. Okay? So, all right. So that's what we'll plan to do. And we'll talk about that then next week. Now, the next thing is sort of where I'm going to be and what my schedule is going to be like. Because for a full-term class, today's the last day of class for Tuesday, Thursday class. Monday's supposed to be the last day of class for Monday, Wednesday classes. Okay, Friday, tomorrow's, yeah. So, let me tell you my schedule for the rest of the term. Okay? Oh, I need to know this too. Are any of you graduating this term? No? Okay. Okay, because if you're graduating this term, I have to have everything in for you by Thursday of next week, 1 week from today, because your grades are due by noon on Friday. If you're not graduating this term, which sounds like all of you, then I need everything in by Monday because your grades are due in on Wednesday at noon. So, unless some of the others come in and they're graduating, yeah, but whether they are or not, you still have until Monday. Okay, so let's back off one more step from there. Tuesday being the last day of class, on that day I will return every lab and every test to you on Tuesday. That means if you have not turned in a lab or taken a test by Tuesday, it's too late. Maybe it's too late. No, that's a song. Okay. But I will be returning everything on Tuesday. So that means let's try to get everything caught up and finished today. And you were asking about this. I think we'll have time. But if not, we're going to have plenty of time on Tuesday. So you can certainly do it then. Okay? If we don't have time today, but you certainly can do it today too. Any questions on that? So let's go over how we're going in. Tomorrow, just like all Fridays, I'm going to be on the Birmingham West Campus from 8 to 12. Okay? Same as always. I'm usually there before 8, and I'm usually there after 12, but I don't want to be too late after 12 because I've got to drive to Georgia tomorrow after I get off. Okay? Now, Monday. Monday is the last regular day of class for full-term students, full-term classes. So I've got 8 to 10 free. Those are my normal office hours on Monday. I've got classes from 10 till basically 4 o'clock almost. Those I'm in class most of that time. And then I'm free again, office hours from 4 to 6. Okay. Beginning Tuesday, this is for regular term classes, that's the first day of finals. Well, I have a final, and if you're in a final, in a full-term class, or mini-term, either one, the final exams start on the hour, not on the half hour. So that means an 8:30 class, your final is going to be starting at 8, not 8:30, 8 o'clock. So don't show up at 8:30 and expect to have 2 hours to work on your test. You won't, okay? You'll have an hour and 10 minutes, or a little bit more than that. You only have 8 to 9:50 to work on the test. So please get to your 8 o'clock classes on time. 8:30 classes, your exams start at 8. So on Tuesday morning, I'll be giving an exam down the hall from 8 to 10, basically. Okay? Then from 10 o'clock until this class starts at 1:15, I'll be in my office. That's not normal, but that'll be starting Tuesday. We'll have this class starting at 1:15. Okay? Whatever we have to do, finish Chapter 8, the lab on Chapter 8, whatever is left to do, we'll be doing starting at 1:15. Okay? And then I'll be here till 6. So you're going to have plenty of time on Tuesday. Wednesday, I have no scheduled exams, so I'll be in my office basically 8 to 6, or somewhere close to my office, 8 to 6. Now, when people come by and make up a test, I usually go to whatever is closest classroom and monitor the test from there. I don't come all the way up here. We just use any closest classroom. So look for me in any classroom between my office and here. I may be anywhere there. Okay, that's Wednesday. Oh, I'm sorry. Wednesday, it's only 8 to 4. Because on Wednesday, I have to go to the Birmingham East Campus because that's when my physics class turns in their work. So I will be there from 4:30 to 6:30. So I'll only be here 8 to 4 on Wednesday and over there from 4:30 to 6:30. Okay? Thursday, I have nothing scheduled except this test. Okay? So I'll be in my office from 8 to 1. This class, the test starts at 1. Now, don't sweat it if you can't be here at 1 because it's not going to take you long to do your test, okay? And you got all afternoon to do it. But technically, we start at 1. And unless I hear otherwise, that's when we'll have our pizza, okay, at 1 o'clock, maybe a little before 1, okay? Now, I will be here until 6. You won't take that long for you to do your test, but I'll be here till 6. Then Friday of next week, back on the Birmingham West Campus from 8 to 12. Monday of the following week, I'll be here from 8 to 6. Be grading papers, getting grades in, all that kind of stuff, 8 to 6. Then Tuesday, we are here. Y'all are through, completely through. We're still here on Tuesday. Thursday, and that'll be 8 to 6 again. Wednesday is when grades are due by 12 o'clock noon. Okay, so I'll be putting the final grades in, but I'll be here 8 to 6. Okay? Then Thursday of next week, I think we still have a duty day, so I'll be here 8 to 6 again. Now, we'll probably have some departmental meetings or something, so I might be back on Birmingham campus, but those haven't been set up yet, so I don't know about those yet. Okay? Then Friday of that week, that's when graduation is. Oh, let me back off there. I have a nephew who's getting his MBA at LSU in Baton Rouge. I think his graduation is Thursday, so I may not be on campus at all that day because my wife agreed that we would drive the grandparents down. They're in their 80s and they live in Huntsville, and they can make the trip. It's hard on them, but they can make the trip. But they don't want to drive in Baton Rouge on graduation day in spring term. Okay, that is a madhouse down there. He graduated his undergraduate there a few years ago, and we drove then too. It's crazy. It's totally nuts. So they don't want to do that. So she volunteered us to drive him. So I will be out I think that's that Thursday, and probably Friday too. I think we'll be coming back Friday. So anyway, that's beside the point. So if any of you were graduating, I may miss her. I don't know if I doubt if we'll be back by 1 o'clock, but I will if I can. All right. Any questions on how we're going to wind this up? Okay. Then let's hit where we left off last time. This is on Chapter 8, Atoms and Periodic Properties, and this is at the very first page, 206. We didn't get very far last time. We talked about Dalton's atomic theory. Here are 5 principles, you might say, statements that summarize his theory. Okay, number 1, all matter is made up of little bitty, tiny little particles called atoms. And his theory was these cannot be divided. Now, I talked about this last time. If you listened to the video, you may not have yet. But way back in ancient times, there was a Greek named Democritus who just reasoned that there has to be some smallest particle of matter. So if you had a piece of iron and you broke it into 2, and took the smaller piece and broke it into 2, and just kept doing smaller and smaller and smaller, at some point, you'd have the smallest piece of iron that you could possibly have. You can't break it any smaller. He called that an atom, which in Greek was from the Greek word that meant indivisible. Okay? A generation or 2 later, here came Aristotle, who said, nah, matter is a continuum. You never get to the smallest piece. It's always that matter, which is a little nuts in today's terms. But when Dalton came along, he said, no, we have to revive Democritus' idea. There has to be some smallest piece of anything. And the smallest pieces would be atoms. Sometimes they're all the same atoms, sometimes they're different atoms, but the smallest pieces would be these indivisible atoms. That's one part of Dalton's atomic theory. Number 2, an element, which you find in the periodic table for some text, is at the back of the book. I think it's in all of your books somewhere. I don't know if they're always in the back of the book. But that's a table of all the elements known to man. Okay? At least man on Earth. Some of these are unknown because they have UNNs or something like that because they haven't been discovered yet. But they have room on the table here for about 118 atoms. Some of them we may not know yet, but they have room for those if they do run into them. Okay? Or maybe they think they've seen them at some point, but they've been very short-lived. So, an element, those 100 and some odd objects, are all made up of identical atoms. Like iron, like oxygen, like carbon, like beryllium, all those same identical atoms. Copper, lead, those kinds. Okay? Different elements have atoms with different masses. Now, this was what Dalton was basing things on. And that's absolutely true. Different elements have atoms with different masses. Hydrogen has a mass of 1, okay? Except very rarely you'll find a hydrogen with a mass of 2, and even more rarely a mass of 3. But he didn't know that then, okay? But nothing else has a mass of 1, 2, or 3. Helium has a mass of 4. Lithium has a mass of 6 or 7. Yeah, they all have different masses. Okay, their atoms do. Up to the heaviest ones have masses of several hundred. Now, I haven't given you units, but they have different masses. Okay? Now, these are elements. Chemical compounds are made of atoms with specific integer ratios. That's why I figured out they had to be indivisible atoms, because they always combine in certain ratios. For instance, water is 2 atoms of hydrogen to 1 atom of oxygen. Always. H2O. Never varies. If it's not H2O, it's not water. Okay? They all have that. Carbon dioxide, 1 C, 2 O's. 1's carbon, 2 oxygens. Okay? Ammonia, 3 hydrogens, 1 nitrogen. Okay? Everything, every compound, chemical compound, made up of atoms and specific energy ratios. Now, some of your organics get really complicated. And this is a simple organic, one of the simplest. Sugar, okay? Fructose, glucose, and sucrose all have the same formula. 6 carbons, 12 hydrogens, and 6 oxygens. Always in those ratios. Always. Some more complex sugars may have some extra things in them, but those 3 sugars are all exactly like that. Okay? How they're arranged, that makes a difference between fructose, sucrose, and glucose. Okay, just how they're arranged in that organization. And then finally, atoms are neither created nor destroyed in chemical reactions. I don't know if you recall from the last chapter, we talked about an electrical currents, okay, that's moving charges. The charges are never used. The energy from the charges are used, but the charges remain. You cannot destroy the charges. The electrons or the ions or whatever it is are not there. The energy from them is used. That's what makes the light shine, the computers run, whatever is happening. That's because the energy is used, but the actual charges are neither created nor destroyed. Well, the same thing for atoms and compounds and molecules. They're neither created nor destroyed in chemical reactions. They're just rearranged. Just rearranged. Energy is transferred. Okay? For instance, those little green leaves right there. They're taking energy from the sun and making chemical compounds. Probably fructose, or one of the sugars. Okay? Then they're also making other things like proteins and other things, and cellulose, other things. They're making all those things from the thing. They're only rearranging atoms. They're not creating nor destroying atoms. They're making new compounds, but it's all from the atoms they already have. Okay? They take carbon dioxide from the air and get their carbon. They take hydrogen and water and oxygen from the water that they pull up through the roots. That's where they get their sugars. C6H12O6. They get all that from the carbon dioxide and water. They're not creating new atoms. They are just rearranging existing atoms into different compounds. So there's Dalton's atomic theory. And what are we doing right now? We're breathing in oxygen, and our bodies are metabolizing the food you ate for lunch or for breakfast or whatever, and metabolizing that means you're burning it. That's why you have a temperature, okay? Because you're oxidizing the food that you've already eaten, and in the process of oxidizing that, you are changing the oxygen that you use is basically burning or oxidizing the carbohydrates that you ate and making carbon dioxide, and that's what you breathe out. Okay? So we are chemical machines ourselves. We are doing the simple process, but we're not creating any new atoms. We're just rearranging atoms within our system. Some of that material we'll make and maybe store to repair muscle tissue, eye tissue, whatever kind of tissue needs repair, skin tissue, whatever. Other things are used for energy, but we're just rearranging atoms to make the things we need. Now, sometimes, quite a bit after John Dalton, one of the, I believe he was a British scientist, J.J. Thomson. There were a lot of good Thomsons. Remember there was Lord Kelvin was, what was that, William Thomson? I believe it was. I don't think there was any kin here, but J.J. Thomson in the late 1800s performed what we call a cathode ray experiment. Now let me see if I can explain to you what a cathode ray is. All right, what you do is you have to pull out as much of the gas out of this container as possible. That's why they show a vacuum pump here. You don't want lots of air molecules or any kind of molecules floating around in there. You've evacuated everything as much as you could, okay? And then what you have here, you put a very high voltage, a positive on this end, that's called the anode, and a very strong negative charge on this end, and then the negative charges go flying down the tube, and that's why you want to evacuate all the air, because these charges, if they hit air molecules, they're going to be arcing and sparking, okay? So you try to get all the air molecules out of there. These basically electrons or cathode rays are flowing down the tube here, okay? Now, like I said, no one knew, but there was something going down the tube there, okay? We now know those to be electrons, okay? So he performed these cathode ray experiments. I can't tell you exactly how he did it, but he discovered that there were these negatively charged particles that were leaving the cathode, flying down here and being collected on the anode, okay? And he knew they were negative charges because this was positive, that was negative, and they were going that way. So they had to be negative. They were trying to balance out the positive charges, but then the high voltage was sucking those on around and keeping them moving, okay? So he discovered these negatively charged electrons. Now, in discovering that, he could determine, because he was taking very careful experiments and measurements, and he was noticing how much was building up here on the anode, how much was going away from the cathode, very, very fine measurements, and so he found out how much charge it took and how much mass was exchanged. So he was able to determine the electron's charge to mass ratio. He couldn't determine how much charge it was. He could determine how much charge it was, how much mass, but he couldn't determine what each individual electron was, but he could get its charge to mass ratio. He identified the electron as a fundamental particle. You can't get any smaller than that. Now already what this did was sort of negate a little bit of Dalton's theory. Remember Dalton? He said indivisible atoms. Well, what J.J. Thomson was doing was ripping off electrons from some of the atoms here, firing them down the tube, and they were collecting there. Okay? So he was dividing, in some sense, those atoms, pulling off the electrons. Of course, his circuitry here, that was supplying more electrons here and taking them away here, so, the amount of charge and then what was building up here, he was able to determine. So, anyway, that was Thomson's discovery. Mostly, he identified the electron as a fundamental particle, negative electron, and measured the charge to mass ratio. All right. Now, here's a little more detailed description of what he was doing. Okay? There's a lot more involved than what we were just showing. But here's how he found out they were negatively charged. Okay? What we have here is your cathode ray. Okay? It was sending the charges down here. But what he was doing was put them through two charged plates here. Okay? Now, those two charged plates did two things. Number one, it narrowed the beam into a very, very, very narrow beam. The other thing it did, because they were charged plates, he could determine what the electrons' charge was, because the electrons were being deflected by those charges. And he knew what charges were on the plate, and it was deflecting the electrons in a certain way, which indicated it was moving the electrons, say, up. That meant if this was a positive plate here, a negative plate there, that would bend the beam of electrons up. That meant the electrons were negative. So his detecting screen was able to pick up that, because he had them in a very narrow band, he could see that that band was being bent. Okay? If there were any positive charges there, they were being bent in the opposite direction. So he was able to determine from this those that were being bent up, the electrons, he could get the deflection dependent on the charge to mass ratio. Now, how did he do that? Well, if you remember what momentum is mass times velocity. He was able to measure the velocity, okay, somehow, measure the velocity of these things, and therefore determine their mass, not each individual mass, but get the overall average mass. So he had the average mass, average charge, he could get the charge to mass ratio. The deflection depended on that, because the greater the momentum it had, then the less it would be deflected. Okay? So he was able to do this. And let's see, I've marked him here 3 times already today. Okay, so good deal. Welcome back. Okay, something else is happening here, though. This is going through a magnetic field. Look at this. There's a magnet. Now, it doesn't show which is north and which is south, but anytime you have a moving charge, you're inducing a current. Okay? So we had moving charges inducing currents. You had a magnetic field, the moving charge in the magnetic field. That current was then also doing some weird things. So it's a pretty incredible experiment that he put together, and he was able to determine with very careful measurement what the charge to mass ratio was. All right. Now, that was late 1800s, probably the 1880s, 1890s. Within another 10 to 15, 20 years, here came Robert Millikan, which I think was another British, an American physicist, okay? Let me see, English physicist J.J. Thomson. I know that Democritus was Greek, English chemist John Dalton. Seemed like for some reason I was thinking he was Scottish, but that would still be English. And English physicist J.J. Thomson, but an American physicist, Robert Millikan, around 1906, came up with a really, really clever experiment. Okay? And here was the source of this experiment. He studied the charged oil droplets in an electric field. Now, we've already shown that if you put the positive charge here, you see from about, oh, they've got it backwards. Do they have it backwards in the book? Yeah, they do. Yeah. This battery's turned around. Sorry about that. I just hadn't noticed it. Okay? So the positive charges were here, negative charges here. Okay? Fairly strong, well, just an electric field there. And he could adjust the field. And what he did, he sprayed Mom or somebody ever had these little things that spray on the perfume with, or cologne or something, a little bulb, and that makes very, very, very tiny little droplets. So he had they call it an atomizer. It's not as small as atoms, but it's making very, very fine droplets of oil. Okay? Now, the only reason for that is just to have something to land the charges on. Okay? Now, he sprayed them out here, but there was only one single little hole in the top here, very tiny little hole, and occasionally one of those droplets would make its way through the hole. Most of them just plated out on top. He's only interested in these few droplets that made their way down. Now, I had a viewing scope over here on the side, and by the way, this is under evacuated all the stuff, was under a vacuum pump, so he didn't want other things interfering here. And as the oil droplets fell, in the presence of this strong electric field, a few electrons, they would pick up electrons, okay? Because electrons would be trying to go from the negative plate to the positive plate. They would pick up a few of these electrons, and then, when they picked it up, then electrons tried to move up because they were repelled by the negative plate and attracted by the positive plate. Well, guess what, team? Those little oil droplets had mass, and he could estimate about what the mass was. Gravity was pulling down on them, but the electrostatic force was pulling up. Now, what he found was, pretty interesting, that these little oil droplets were all about the same size. Some of them moved, basically slowed down. Some of them just kept going. They didn't get any charge. Those that slowed down, they may have picked up 1 or 2 charges. Those that stopped, they may have had 3 or 4 charges. And then those that started rising, they had extra charges. But all these droplets, because they're all about the same size, they traveled at very distinct velocities. And that's what he was able to measure, because in his viewing scope, he had these lines through there, and each one represented a centimeter of movement, and he could time and see each droplet, how much time it took to move from one to another, and figure out how many centimeters per second they were falling. They were all about the same size, and then he came up with, well, the ones that slow the least may only have 1 charge. Those that slow a little bit more have 2 or 3. Yeah. So he was able to distinguish how many each charge would do, and therefore he was able to do the charge on the droplets was a multiple of the electron charge. And he was able very carefully to make the speed of every one, and the speed was always here, here, here. They weren't everything in between. They were very distinct speed. So he could count down. This would have been the smallest change of speed, may have been 1 charge, 2 charges, 3 charges, and so on. Okay? So by his figuring out how many charges and Thompson's result from mass to charge ratio, he was then able to get the electron mass. You can't measure electron mass on a scale. There aren't any scales sensitive enough to do that. But through a really interesting experiment like this, you could. Now, this is rather bizarre, but when I went back to grad school, I started in a winter term after I got out of the Navy. Went back to Georgia Tech where I had done my undergraduate and just tried to piece together a schedule. And I was a physics major. There was one math class that I had never been able to take, and they would allow me to take that. It's a 400 level course, but I could take it on my master's, so I took that one. And there were only 2 physics courses I could manage to get scheduled. And then my brother insisted that I try to do an economics course because he had been an economics major. He said, "You'll love this guy." A boring course. Okay, I didn't say that, did I? But anyway, those were my 4 courses. Well, this one and only one physics course I was able, no, there were 2, but one of the physics courses I was able to take was a laboratory course. That's all we did. We did lab, I think 4 or 5 different labs over a 10-week term, okay? And one of the labs we did was the Millikan oil drop experiment. So I actually got to see these droplets change the speed, make the measurements and stuff, and we saw the very thing that Millikan saw that we could determine that. Very carefully controlled experiment, but we were able then to estimate our results, and we came fairly close. It wasn't right on the money, but we came pretty close. I say we, there was another. So here was Thompson's result. He got a charge to mass ratio for an electron of 1.7584, fairly precise number, times 10 to the 11th, wow, huge number, coulombs per kilogram. Well, that's why, because a kilogram is a huge amount of mass, okay? But Millikan then, with his result, then was able to actually determine the individual charge on an electron, and that was 1.60 times 10 to the minus 19 coulombs. Excuse me. So, combined then, you could then get the electron's mass, which was then, using this and that, you came up to 9.11 times 10 to the minus 31 kilograms. Like I said, there's no scale on Earth that can measure anything that fine. And yet, he was able to do that. by calculation. Okay? It's just about like, remember when we did the pendulum experiment? You couldn't measure the speed of that pendulum at the bottom, but by knowing the energy at the top, the energy at the bottom, you could calculate the speed. And you could get it pretty correct. Same thing here. No one could measure the mass, but by measuring charge to mass ratio, Thomson did. Millikan got the charge, found out what that was, and then combined that with the charge to mass ratio, you could calculate the charge. Incredibly tiny amount of, calculate the mass. Incredibly tiny amount of mass. Millikan's oil drop experiment. Okay? Then came Dalton. Okay? We already talked about Dalton. Here they bring them up again. Actually, he came before this, so this is sort of a review. Dalton said atoms were indivisible. Okay? Thomson-Millikan experiment showed that the electron mass is incredibly small, but could not determine a volume at all. No measurable volume. So, if that was a negative charge, where was the positive charge? Well, Thomson had an idea for that too. He called it the plum pudding model. He said the electrons were sort of embedded in a blob of positively charged matter like raisins in a plum pudding. Okay? Now, I'm not British and I've never had a plum pudding that I know of. Okay? But what I think of is bread pudding. Have y'all ever had that? And raisins you do have in bread pudding. It's scattered throughout. So I just think of bread pudding rather than plum pudding. And this is what they figured for a while. The negative charges must be just somehow mixed in with the positive charges. Negative charges have almost no volume at all. Very small mass, so they must just sort of be scattered throughout the dough, you might say, of a bread pudding, in every now and then like a raisin would be. Raisins are much bigger, but you get the general idea. Well, here came Ernest Rutherford. Now, he was another Brit. Pretty sure they don't say it here, but I'm pretty sure it is. And by the way, before I get any further, in case I tend to forget it, the discovery of the electron, the Crookes tube is what we later called the cathode ray tube. Okay? So here's another person you could write on if you haven't chosen a paper topic yet. Already in this chapter, think about it. We've hit Democritus, we've hit Aristotle, we've hit Plato, we've hit John Dalton, we've hit J.J. Millikan, we've hit J.J. Thomson, Robert Millikan. Man, they just keep coming. And then on this little blurb at the top of the page, English physicist William Crookes did the Crookes tube. Then you have Michael Faraday is mentioned. J.J. Thomson is mentioned. And then the oil drop experiment, of course, is Millikan, but wow, there's just so much here in just such a small space. So I just wanted to mention that before we moved on. So here's your Ernest Rutherford, okay, around 1907. So things happen more rapidly. Millikan was around 1906. Thomson had been late 1800s. Millikan 1906. And now in 1907, Ernest Rutherford. Now here's what his experiment was. He was able to isolate what they call alpha particles. I don't know if y'all are familiar with alpha particles, but it's basically the nucleus of a helium atom. Okay? Helium has 2 protons and 2 neutrons in its nucleus. Okay? For an atomic mass of 4. Usually has 2 electrons floating around in a cloud. Well, somehow Rutherford and others before him had been able to strip off the electrons, leaving you these alpha particles, which were positively charged, not hugely massive, but much bigger than electrons, that they could fire. Because they were charged, they could put them through the electric fields, between electric fields, and they could give them pretty good amounts of energy. Okay? So what he did, he took gold foil. Now, gold is pretty expensive nowadays. It was valuable back then, but not nearly expensive. But gold has this property. You can roll it into just incredibly fine sheets. In fact, have you ever heard of the term gold leaf? Okay, gold leaf is just incredibly thin sheets of gold that you can take with a device like a metal rubber thing that you might do and just rub it on wood or something else on this very fine gold thing, and you leave just a very thin layer of gold, and it makes your picture frame look like it's gold, or it makes whatever you're trying to do look like it's gold. You're using very little gold because it can be rolled into such fine sheets. So that's what he has, gold foil, like aluminum foil, only thinner. Scattered alpha particles off of gold foil. Now, what you would expect to happen if it was Thompson's plum pudding model, you would expect most of those alpha particles to be deflected backwards, okay? Because the plum pudding would keep them from getting through. Gold is pretty dense material, it would keep them. Here's what he found out, much to his surprise, is that most of the particles pass through without any significant deflection whatsoever. And gold is a pretty dense material, and yet they went right through it. Right through it, okay? A few were scattered way back at very large angles. He was expecting most of them to be scattered back, but a very few were scattered at large angles. What was his conclusion? The atom's positive charge that would repel the alpha particles, which were positive charge, and he thought that would just be all set back, resides in an incredibly small but very massive nucleus, okay? And around that was basically empty space. The electrons were in that empty space, but there was nothing else there. And for most of the alpha particles to just go right through without anything meant that as dense as gold was, there was nothing to prevent it. So those nuclei, that's what we call them later. Conclusion, the positive charge resides in a very incredibly small but very massive nucleus. Later, they were able to identify the positive charges in there were things called protons. Positive charge and very massive, especially massive compared to an electron. Electron has very tiny mass, 10 to the minus 31 kilograms, incredibly tiny. Whereas protons were like 10 to the minus 28, so 10,000 times more massive than the electrons were. Finally, then, 25 years later, James Chadwick, also British, found that there were some neutral neutrons, neutral particles in that nucleus, and these he called neutrons. Neutral, they had no charge, but they were there in the nucleus as well. So the nucleus is really packed with matter, but has very, very, very small volume, okay? Incredibly small volume, incredibly massive nucleus. So James Chadwick was yet another. Okay? Here is basically Rutherford's experiment. Now they had discovered their nuclear particles, and one of these nuclear particles was the alpha particle, which is two positives. They didn't know this at the time, but a double positive charge, because it had two protons, had two neutrons, they didn't realize that, but two protons. And they fired this through the gold foil, and lo and behold, most of it came all the way through. Never even deflected. Okay? A few others were deflected slightly, but a few were sent way back to the back. Those are the ones that actually came close enough to a nucleus to bounce back. Most of them made their way through without any deflection whatsoever. So that was Rutherford's experiment. It's called the gold foil experiment, and he was able to determine plum pudding was not the right model. Plum pudding would have had most of them being deflected backwards. This had almost none deflected backwards. Okay? So here's what you've got. This is the picture. Now, I don't know if this is realistic or not, but it's a pretty good picture. If these were your gold atoms, the nucleus would be in a tiny, 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 tiny little space in the middle and the electron cloud around it. Okay? The electrons have almost no mass, almost no volume, no measurable volume, so there's nothing to prevent that. But the nucleus, because these are alpha particles, positive particles coming in, only when they hit a nucleus would they be deflected backwards. Most of them made their way all the way through. Only those that happen to hit one of those nuclei would bounce back. So they were able to determine approximately the size of the nucleus. What they didn't know was how many atoms thick the gold foil was, but they could estimate that, I guess. So very few alpha particles got deflected back. Most of them went zooming right on through, never hitting any nucleus, which indicates, wow, the nuclei are very, very small. Okay? Now, this leads to how we talk about atoms. Okay? We give every element an atomic number. Okay? And basically, this atomic number is how many protons are in the nucleus. If there is one and only one proton in the nucleus, that's hydrogen. No way it can be anything else. If there's two and only two protons in the nucleus, then that's helium and nothing else. 3 would be lithium, 4 would be beryllium, 5 would be boron, 6 would be carbon, whatever. You just keep adding, and the number of protons determines without any exception what the element is. That's determined by the number of protons. That's called the atomic number. Now, when they first started this, they didn't know all of them. So there were some blanks in their chart. But later they were filled in. When they wrote this slide, they said 113 elements had been identified. I wouldn't be surprised if I don't think we're up to 118 yet, but maybe a few more have been identified. The number of protons is going to equal the number of electrons if you have a neutral atom. Of course, not all atoms are neutral. If you have a positively charged atom, that means that atom has lost an electron. And that happens. You may even have lost 2 electrons. Very rarely could you lose 3, but it could happen. Or that atom could have gained an extra electron, and that happens frequently to be a minus 1 charge. Or gain 2 electrons, which would be minus 2 charges. Very rarely, but occasionally could gain up to 3 electrons. But if they have the number of protons equaling number of electrons, you have a neutral atom. But there are different, and I said this earlier, I'm going to recall it now, different hydrogen atoms or lithium atoms or boron atoms or other atoms that have slightly different masses. Okay? What happens then, if it's a given element, it has the same number of protons, but you could have different number of neutrons. Let's go to the simplest atom, that's hydrogen. Most hydrogen atoms only have a single proton and 1 single electron. Like 98, 99% of the hydrogen atoms, single proton, single electron. Electrons going anywhere it wants to, proton pretty much stays in place. However, about one time every 200 or 300, you'll find 1 single neutron with that proton in the nucleus. Proton and a neutron with that 1 single electron. Okay? Then you have, because it's doubled its mass, because the mass of a neutron is only slightly bigger than the mass of a proton. Not much. Very, very slightly. So basically you've doubled your mass, and that's called deuterium. Deuterium. And then like one time over every 10 or 100,000 times, you'll find two neutrons and one proton. Because that's tripled the mass of the normal hydrogen, they call that tritium. Okay? So those would be three isotopes of hydrogen. Regular hydrogen most of the time, deuterium every now and then, and incredibly infrequently tritium, which has two. So it's the same proton. For it to be hydrogen, it's got to have one proton. If it's no neutrons, it's regular hydrogen. One neutron, then it's deuterium, and two neutrons would be tritium. Okay. Now, and they're giving the names here. The other name is hydrogen 1, hydrogen 2, and hydrogen 3. Now, this is what the standard nomenclature is. You put the symbol for the element here, okay? The subscript number here is how many protons. Hydrogen is always 1. So the subscript is always 1H, 1H, 1H. The superscript is the atomic mass, okay? And this would be how many particles are in the nucleus, okay? If you have no neutrons, that would also be 1, because the only particle in the nucleus is a proton. So it would be 1 hydrogen. If you have 1 neutron there, the total mass of the proton would be 2, one of them being a proton, the other being a neutron. And that gives you deuterium. Or if you have 2 neutrons there, which is very rare, but it does happen, then you'll have total atomic mass of 3, but only one of them is a proton. So that would be tritium. So what you do, you put the symbol for the atom here, its atomic number is down here, how many protons, and the mass number is up here. How many total nuclear particles do you have? Protons plus neutrons. Okay? And you'll notice here, the number of neutrons is the difference between those numbers. Here your difference is 0, so you have no neutrons. Here the difference is 1 with 1 neutron. The difference here is 2, that means you have 2 neutrons. The difference between the mass number and the atomic number is the number of neutrons. So that's what we mean by isotopes. Iso means same, so this is same element, but different. Same number of protons, but different. So you can think of the tope as being protons and the different numbers of neutrons. Okay. So, this is almost saying the same thing again, but we'll say it again. Atomic symbols and the masses. Your mass number, and we said this before, is the total number of protons and neutrons. Now let me back off and say this. Hydrogen is the only atom I know about that may have no neutrons. Anything bigger than hydrogen is usually going to have at least 1 neutron. Most of the time more neutrons than protons, but sometimes the same number. But very rarely, hydrogen being the exception, we have more protons than neutrons. Now, we also use what we call an atomic mass unit. Now, back when I was in school, this was called an AMU, for atomic mass unit. Now they are being much more concise with it and just calling it a unit, an atomic mass unit. Now, they picked sort of, to me, it was a fairly strange thing. They said 1/12 of a carbon-12 isotope mass would be 1 U, okay? You say, but wait, are all protons and neutrons the same? Yeah, we think so, but you see there's also some other materials that are inside a nucleus that back when they determined this, they didn't know for sure what the differences were. So there are some differences. But yeah, protons and neutrons are all the same. Not as each other. They're all the same. So this is what we call 1U, 1/12 of the carbon-12 isotope mass. Now, what's your atomic weight? That's the atomic mass of an element averaged over the naturally occurring isotopes. Like I just said, hydrogen has 3 naturally occurring isotopes: regular hydrogen, deuterium, and tritium. And because these are so small, the average atomic weight for hydrogen is just slightly more than 1.00 something or other. Very slightly more. And that's just because there's not much of these other 2s out there. Okay? So here's what we've got. Same picture as before. So nothing new here. This just shows that the atomic number is here, how many protons, and the mass number is here, which is the total number of protons plus neutrons. So this would be 1 proton, 0 neutrons, 1 proton, 1 neutron, 1 proton, 2 neutrons. Okay? So nothing new there. Same slide we saw before. Okay. Here is their example on this. Nitrogen. Okay? Nitrogen is a gas, fairly light gas, and by its figure here, you tell me what this stands for. What does this tell you about nitrogen? The little 7 is a subscript in front. Number of, it's the atomic number.
Atomic number.
Okay, and what does that tell you about it?
It's 7 in nitrogen.
7 protons in nitrogen.
Yeah.
If you have 7 protons, you're nitrogen. No question about it. No other element has exactly 7 protons. What does 14 tell you? It's the mass number. Okay? And what's the difference between those? 7 of this mass is protons. You know that.
Right.
That means the others are?
Electrons.
No, electrons don't count. They're too small a mass. Neutrons is what's in the nucleus.
Right.
So the other 7 are neutrons. And most nitrogen out there, like 99.63% of the nitrogen out there, is in 14. Okay? 7 protons, 7 neutrons. Okay? However, 0.37%, that's 0.0037, so 37 out of 10,000 nitrogen atoms will have 1 extra proton. I mean, 1 extra neutron. Because all nitrogen has 7 protons, but this one has an atomic mass of 15, so that means it has 8 neutrons. So that extra neutron only shows up 37 times out of 1,000. Okay? 30.37% of the time. Okay? Well, the actual atomic mass of this is 14.00307. Just barely over 14. The actual atomic number of this is 15.00011 units, atomic mass units. You multiply this percent by its mass, that percent by its mass, add them up, and basically you get 14.0067 units, or atomic mass units, for nitrogen. Because nitrogen only has these 2 naturally occurring isotopes, and the average of them is 14.0067. See, it's slightly more than the mass of nitrogen 14, considerably less than the mass of nitrogen 15, but because there's so little 15 out there, that's why it's skewed toward the 14. Okay? Let me get Seth here. You are below the blue line. Right there. Okay. So that's how we get the atomic masses or atomic weight of each of the elements. Okay? So if you look at your periodic table or any listing of chemicals that give the atomic mass and the atomic weight, and you'll see that. I don't know if you have the table of atomic weights on the inside cover. You may not, but you should have a periodic table. Again, the number at the above, now this is sort of backwards from what they did here. The number above each element's symbol, that's the atomic number. 1 is hydrogen, 2 is helium, 3 is lithium, 4 is beryllium, 5 is boron, 6 is carbon, 7 is hydrogen, 8. That's the number of protons in that given element. Always. You can't have a different number of protons. But the number below it, hydrogen is 1.008. That means for every 8 out of 1,000 hydrogens, you're going to probably have one neutron. Most of the hydrogens have no neutrons. Helium, 4.003. That means most helium have 2 protons. They all have 2 protons. Most have 2 neutrons as well. That means about 3 out of every 1,000 will have an extra neutron. Okay? Not often. Okay? Now, lithium, because its atomic number is 3, that means 3 protons, its atomic mass is almost 7. That means most lithium is going to have 4 neutrons, but about 1 every something about 15 or so will have 6. 3 neutrons. Because you see the number is a little bit less. The normal number is 7. It's 4 neutrons, but every now and then you only have lithium with 3. And you can keep on down the list there. And the difference between the atomic number, which is always an integer, and the weight, which is underneath it, that's going to be approximately the number of neutrons. If there's anything other than a whole number, then it's likely to have an isotope. Okay? Like 15, nitrogen 15 is a rare isotope of 14, and that boosts up this to a little bit more than 14. Okay. There is a little case study at the top of page 210 on discovery of the nucleus, and this is again going over J.J. Thompson's and Ernest Rutherford's work. Okay. Now there is a table in your text, table 8.1. It's not shown on the slide set, I don't think. No, not at all. Let me back up a slide then and put it here. And this table is selected atomic weights calculated from mass and abundance of the isotope. So they showed regular hydrogen here and deuterium here. The mass compared to carbon-12 and then the natural abundance. So 15 of every 100,000 hydrogen atoms will actually have an extra neutron. Okay, that's what this tells you. In beryllium, there's only one naturally occurring isotope, and so 100% of that. Now, it still isn't exactly 9. That's because there's some other variation in the atomic mass. We won't go into it now. Here's nitrogen with the 14 and 15, the one we saw right here. Oxygen actually has 2, one regular isotope and 2 slightly heavier isotopes. The regular isotope is oxygen 16, that's 99.759% of the time, whereas 17 is 0.03% of the time, where 18 is actually more prevalent than 16, than 17 was, and that's 1 out of every, 2 out of every 1,000, 1 out of every 200 or something like that. And then fluorine only has 1, neon has 3, aluminum is only 1. So that's just a few randomly, I guess, selected ones to talk about. There's a concept applied here on atomic parts, and it's sort of talking about the same thing, so I'll let you read that on your own. Okay, the next slide is then going to deal with the classical atoms. And they put the atoms in quotes. I don't know exactly why. I would have put classical in quotes and left atoms alone. So these are the predictions from the early classical theory. Okay? Electrons orbit the nucleus. We know they do. They're flying around the nucleus, just randomly flying around there, no special order or anything else. Because they have a curved path, because the nucleus is a positive charge, they're negatively charged, it's always pulling them in. Because they're a curved path, that means there must be an acceleration to create a curved path. Well, accelerated charges are supposed to radiate. If they radiate, they're losing energy. If they're losing energy, they're spiraling into the nucleus, and this says that atomic atoms cannot exist. Whoa, but we know atoms do exist. So there's something wrong with this theory. The classical theory had some big problems with it. Experimentally, we know atoms do exist. Classical theory says they can't exist. A new theory is needed. Now, this was one of the little bugging questions that physicists had at the turn of from the 1800s to 1900s, the beginning of the 20th century. Physicists thought, well, the chemists still have some work to do, but not too much. They've discovered most everything there. Most of the other biological sciences, they're always discovering new things. But guess what? We physicists, we just about have it all wrapped up. We have Newton's laws, we have thermodynamics, we have it all. We just about got everything sewed up in a nice little bundle. We just got a few nagging problems like this, but look, it's not going to take us long. We're going to have it settled, and physics will be done. We can tie a bow, present it to you, go from there. We'll just teach you that from now on. It's tough enough as it is. We'll go from there. Well, we need this one little place, we need a new theory. Here came quantum mechanics. And once it showed up, everything got blown out of the water because it predicted things no one even conceived of before. Max Planck was one of the originators of this. I'm pretty sure he was a German physicist. Let's see if I can find him here. And by the way, you just keep seeing all these names. One that I almost just skipped over was Maxwell's equations of electromagnetic radiation. I think I mentioned him before. James Clerk Maxwell. Spelled like it's clerk, but it's pronounced Clark. The Scots do that kind of stuff. He was a Scottish physicist. Incredibly great mind. Okay? And here was, they start with Niels Bohr. We're going to get to him later, a young Danish physicist who visited Rutherford's laboratory in 1912, became interested in some of this. But before that, Planck and Einstein had come up with this, what they call the quantum concept. So Max Planck, in 1900 or so, introduced this idea of quantized energy. Now what they mean by that energy always came in tiny little packages. Tiny little packages. It didn't come as a continuum. See, before this we thought energy was could be anything. What Planck discovered, energy always showed up in discrete little packets. Now, sometimes they were so mixed together you couldn't distinguish them, but they did come that way. Okay? Einstein in 1905 found out that light itself was made up of quantized photons. Photons would be that little unit of energy. That's what they called a photon, light energy anyway. And Einstein discovered that. Now, because of that, we can have these fluorescent tubes, okay? And we'll get to that a little bit later. I think I've already mentioned those before. Here's a key, and this came from Planck. Higher frequency photons means you have more energetic photons. Higher frequency meant higher energy level. So therefore, he came up with this formula. Very simple formula. The energy of a photon, that's a unit, a quantized unit of light or other energy. The energy of a photon is this constant. Now, what he did, he said it was proportional to the photon frequency. Photon frequency. I don't get photons and protons mixed up. I almost said it wrong. Photon is a little unit of energy. Proton is a building block of matter, okay? A constituent of the nucleus. So basically Planck said that the energy given off by a material is proportional to the photon frequency. The photon energy was proportional to the photon frequency, and that constant proportionality he calculated to be somewhere in the neighborhood of 6.63 times 10 to the minus 34 joule seconds. Whoa! Okay, energy is measured in joule. By the way, a joule is a tiny amount of energy. And then frequency is measured in per second, so you have to multiply joule second by per second to get the seconds to go out, and that leaves you energy in joules there. And now we've got something 10 to the minus 34 joule seconds. That is an incredibly small number. Because a joule is already a very small quantity. Okay? So this was Planck's law. Okay? Revolutionized. It seemed so simple, it changed everything. And Einstein built on this and saw that light itself was made up of quantized photons, following this formula. Okay. Now it seems like here they jump a rabbit, okay? And before we do, let's go back and do a calculation or two with example 8.1, okay? What is the energy? So we're looking for E. Let me get my pen set up. So what is the energy? This is the unknown here. All right. What is the energy of a photon of red light, okay, with a frequency? So the frequency for red light is 4.60 times 10 to the 14th hertz. What a hertz is a per second. A hertz is a second to the minus 1. A per second, 1 over second. Okay? Now, what is the energy of that? Well, we have to use Planck's constant. The H here is 6.63 times 10 to the minus 34 joule seconds. A very, very small number. Okay? So this energy is in H times frequency. I said H and wrote lambda. What's wrong with my head here? I don't know. I'll tell you one thing. It's hungry. Because I had students after my last class that stayed and asked questions, needed to print papers, that did this, that. Huh?
So you need to take the test now and leave you alone. You need to eat.
Well, I got to eat just a little over half of my salad. Didn't get to touch my sandwich or touch my fruit, so I am hungry. Okay. but I can live. I need to burn some, but it doesn't feel good. Okay, so Planck's constant is 6.63 times 10 to the minus 34 joule seconds. Multiply that by your frequency for red light, which is 4.60 times 10 to the 14th hertz, which is per second. So I'm going to put 1/2 okay? Well, obviously here the seconds will cancel out. One's in the numerator, one's in the denominator, so they go. And then when you multiply 6.63 times 4.60, you get 2 point something another, maybe 3 point something. So what do you get? 3.05, is that what you said? 3.05, and that would be times 10 to the, okay, when you combine these units, that's almost a minus 20, but because you had an extra digit there, it's a minus 19 joules. That's an incredibly small amount of energy, but that is what you get with Planck's law, okay? Energy is equal to h nu. Now, the next one says, let's do a photon of violet light. So I'll put violet light in violet or purple, okay? So this will be the frequency for violet light is 7.30 times 10 to the 14th. 7.30 times 10 to the minus, positive 14, sorry. Positive 14. Okay? That's the frequency. And that's per seconds or hertz. I'll put hertz because it's just about as easy to write. So you plug it in the same way, but this time it'll be 6.63 times 10 to the negative 34.
7.30.
Second?
I said multiplying
By 7.30 times 10 to the 14th. Okay, this is joule second. I can't write. 4.60 times 10 to the 14 per second. Seconds cancel out. And what do you get?
4.8.
4.80.
I multiply 6.63 times 4.73.
Yeah.
7.30. And I need the engineering notations. And I got 4.8.
Right. I put the wrong one down. I was looking back in the wrong place. 7.30. And what do you get? 4.8 something.
4.83.
4.4. Okay. Times 10 to the negative 19 again. Joules. Okay. So your energy jumps from between red and violet. It goes between 3.05 to 4.84. Both times 10 to the minus 19, but you're just looking at relative. That's, better than a 50%, well, not 50. Fairly decent amount of increase in energy between red light and violet light. Now think about this. What's just beyond violet? Ultraviolet. Ultraviolet is what causes skin cancers, cataracts, aging of skin, because it's higher energy, does more damage to your skin or other things. The infrared, which is below this, is just low-level heat energy. It really doesn't hurt anything at all. It can get too hot maybe, but by itself is not anything bad. So 4.84 times 10 to the minus 14. The other was 3.05 to the minus 19. Okay. So let's go back to atomic spectra. This is the one that seems to be jumping just from out of the blue, but it does tie together. They introduced with this concept of black body radiation. Basically, it's saying this: anything that's out there that has absorbed radiation is going to be emitting radiation. And the black body radiation is basically a continuous radiation distribution. Okay, if something's out there getting hot, then it's going to be producing this heat. Okay? Depends on the temperature of the radiated object. Something that's getting very, 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 very hot might be blue heat. Okay? Something that's getting just relatively hot could be red heat. Again, following the color of your energy. Depends on the temperature of the radiated object. It's a characteristic of solids, liquids, and dense gases. The rest of the gas that's up there in the fluorescent tubes are a mercury vapor gas. Pretty dense gas. Okay? That's black body radiation. Solids, liquids, dense gases, lots of things interacting there, just producing a continuous radiation distribution. However, if you have very specific elements or things like that, then your emission is a line spectrum. The emission is at characteristic frequencies. Okay? Now, seems like to me this diffuse matter, incandescent gases, belongs up here. I don't know why it's down here with the line spectrum. Maybe there's a reason for it, I don't know. It just seems like to me this is more black body radiation. But the illustration they give here is the Balmer series for the hydrogen lines. If you've got pure hydrogen that you're energizing and giving a lot of energy, you're going to see the line spectra come off of hydrogen in a very specific pattern that was early detected and described by a guy named Balmer. So there's another potential paper topic. All right. Now this, again, is talking about more black body radiation, diffuse matter, incandescent gases. If you have light from a just general old light bulb, most of the time that's coming from a heated filament, which could be largely titanium, but you also have argon gas in the bulb, so that's interacting with it. The glass is interacting with it. It's just a characteristic of solids, liquids, and gases. You send that through a prism, you split it, and you see the various bands, but it's a continuous spectrum. Red, orange, yellow, green, blue, indigo, whatever that is, and violet. Okay? That is your light spectrum. Naturally occurring white light always comes up in some type of a spectrum like that. However, if you have a very specific object, like I think this represents all I can think of is calling it a neon tube. It's not that. It's a single specific gas, like neon or argon or something like that. And you send light through that, or also a laser type thing. One very specific thing. Send that through a slit, through a prism. Now you get specific lines of color, not a continuous spectrum. Continuous spectrum would be, a distribution would be your black body radiation. Your line spectra indicate this is more a single gas. Okay? Now, not real clear on these colors, and I guess they have them right. I just don't know what this one is. Okay? Maybe this is supposed to be ultraviolet. I don't know. Violet would be at the top, blue next, and orange somewhere down the way there. Okay? This is leading to the Balmer series. So let's talk a little bit about what the Balmer series is. Not yet.
What time take the test?
5:15. Got a little bit of time left, don't we? Way too much, right? I didn't say that, did I? What is it, just a little after 3? Let's plan to take a break around 3:45, is that okay? Wait, is that right? No, I think we need to be a little later than that. 4 o'clock? Well, we can take a break anytime you want to, okay? Normally we'd be stopping the class at
3:15.
No, 3:45. 3:45 would be right. So let's take a break around between 3:30 and 3:45. Okay. So let me know when that pops up. Okay. So before we get to the Balmer series, we need to do a little bit about Bohr's theory. Now this is where, in your book, is 8.2, the Bohr model. Okay. Niels Bohr was a young Danish physicist, visited Rutherford laboratory back about 1912, became very interested in questions about the solar system model of the atom, okay? And that led then, combining things that Planck and Einstein had done with the quantized nature of energy, which is quantum mechanics, they began to put together these concepts. And like we said, the year 1900, Max Planck, quanta, photons, okay. Here, I'm sorry, I jumped off onto the line. Okay. But here's Bohr's theory. I'm sorry, I got on the wrong page. I was looking at Bohr's model, not Bohr's theory. All right. The book's a little wacko here. Before we get to Bohr's theory, let's back up and do the atomic spectra here. I don't know why they left off. They don't say anything. Okay. They just mentioned Balmer series on the slide, but don't say about it. Here's what Balmer came up with. 1885. This is long before quantization, quantum mechanics was thought of. A Swiss mathematics teacher named J.J. Balmer, just a math teacher, okay, not really all that big of a scientist, was studying the regularity of spacing of hydrogen line spectra. He was able to develop an equation that fit all the visible lines, okay? And by assigning values n of 3, 4, 5, and 6 to the 4 lines, he found the wavelength fit the equation, and here was his equation. Let me go back to my dark. Okay. 1 over lambda, which is the wavelength, is equal to some capital R, some number R, times 1 over 2 squared minus 1 over n squared. That was Balmer's equation that he came up with. Okay? Now, R is a constant, and that constant is 1.097 times 10 to the 7th and I think that's supposed to be a per meter, 1 over meter, but let me see. Doesn't make any sense for that to be liter per meter. That makes no sense. I think it's 1 over meter. Okay? Yeah. Okay. Because, yeah, wavelength is measured in meters, so yeah, that makes sense. So, 1 over lambda is equal to 1.097 times 10 to the 7th, 1 over meter, Okay. Times 1 over 2 squared minus 1 over let's see, I've got to, I didn't write this down. 3, 4, 5, and 6. N equal 3, 4, 5, and 6. So let's start with 3 squared. Okay. If you're doing this on your calculator, okay, now this is a 1. Those are supposed to be a parentheses, just a really ugly parentheses. Okay. All right. So, 1, I'm going to tell you the easy way to do this on your calculator. 1.097, now your EE or EXP, and then you type in 7. That's a 7. It's a pretty ugly 7. But let me make it a little clearer. Okay.
7.
That is a 7.
All right.
Positive 7. Okay. Times, now open a parentheses. Okay. And put 2 squared, and then hit the 1 over x key, or x to the minus 1 key. You see that on your calculator?
It's taking an EX.
Huh? Not EX. It's either x to the minus 1 or 1 over x. Let me see if I can see it.
I said
X to the minus 1. Okay, 2 squared, and then hit that key.
taking it, just
Yeah.
press it down.
No, it's just that key, not second.
Okay.
Okay.
Like that.
Huh?
I said good.
Okay. Minus, you had open parentheses, 2 squared, hit that key, minus 3 squared.
You want me to close the parentheses or no?
No, wait. You open parentheses, 2 squared, 1 over x, minus 3 squared, 1 over x. That key.
Okay.
Then close parentheses,
Parentheses
hit equal,
equal.
and then hit that key one more time. That 1 over x key.
And equal.
Yeah. What do you get?
0.005. So 5.98.
Okay. Say that last thing that you said.
I'll just move the decimal 3 times, or you can keep the same.
Okay.
The same is 0.005. And if you move
Okay.
the
Something seems a little bizarre about that. Supposedly that comes up to the lambda should equal 6.6 times 10 to the minus 7. And that would be meters. Okay? So, do you get that or not? Okay. Let's try it again.
Yeah.
Okay. 1.097 EE or EXP 7, right?
All right. Got
Times, open parentheses, and you can go and write 4, 1 over x, right?
X to the negative 1.
X to the minus 1, right?
All right.
Minus 9, x to the minus 1.
Okay.
Close the parentheses, equal. Okay? Then hit your 1 over x key one more time. X to the minus 1 key.
656.
That?
Yeah.
Okay, times 10 to the minus 7? Got it.
Got it.
Okay. Now we'll do the same thing. That's,
Visually,
what's that?
as it is calculated, it's sensitive.
Yeah. The next one is a blue-green line, so I will do that in blue-green. Maybe this color. And that time we'll do a 4 down here. Same thing, 1 over lambda will be 1.097 times 10 to the 7th, and that's 1 over meter, okay, times 1 over 2 squared minus 1 over 4 squared. And that would be just as easy to do 1 over 4 minus 1 over 16. Or 4x to the minus 1 minus 16x to the minus 1, close parentheses, stop. And if you do the same thing you did before, in that order, you should get 4.8 times 10 to the minus 7 meter. That's the wavelength of the blue-green line. Okay? Then you do with 5 squared, and you would get the violet line, the first violet line, and that'd be 4.3 times 10 to the minus 7. And then you do n equals 6, and they actually do that one in the book. And you get 4.11 times 10 to the minus 7. Okay? Now, if you'll notice there, the 4.13 and 4.11 are getting really close together.
Right.
So it gets harder and harder to distinguish because after a while they start running together. But the ones you can see, this works really well. Okay? This was great, except it only worked for hydrogen. Okay? It did not work for anything but hydrogen. So it was amazing that Balmer came up with it. And the interesting things are these various n's here, 3, 4, 5, 6, they represent energy levels of your energy distribution, and those were your photon jumps were between those levels. Okay? So with that done, that's the Balmer stuff. Now here is Bohr's theory. 3 rules for Bohr's theory. The first rule, electrons only exist in certain allowed orbits. So when I was saying before the electrons were flying around randomly, that's not quite true. That was what they thought originally. Now they say that electrons only exist in certain allowed orbits. There's one orbit close to the nucleus, relatively close. There's another orbit slightly further away, then another. They're only allowed within that allowed orbit. Okay? Within the orbit, the electron does not radiate at all. Even though it's following a curved path and everything else, it's not radiating. So therefore, this problem back here that you were dealing with here, that a curved path means an acceleration charges radiate, electrons lose it. You avoid that. They do not. Okay? That was the first part of Bohr's theory. Niels Bohr, that young Danish guy. Okay? Within an orbit, the electron does not radiate. Okay, we just said that. Okay, only exists in certain orbits. One orbit doesn't radiate. The radiation is emitted or absorbed when you change the orbits. Okay? And I think I explained that to you before by explaining why the fluorescent light produces light. Because you have high energy ions, plasma, flying up and down those tubes, and when it does, it excites and it jumps up in orbit. The electrons will jump up in orbit in that phosphorescent material when the energy is close, and then when the energy passes, it falls back down again. And that then emits a quantum of light. And that's why we get the light from the fluorescent tubes. Radiation is emitted or absorbed only when changing the orbit. Absorbed, you jump up in orbit. Radiated when you fall down in orbit. Okay? And when you do fall down, there goes a photon of specific frequency, and that's what is happening constantly with those lights. Okay? Here's what you were just calculating. It's a lot like Balmer's series. It is Balmer's series. The numbers come out right. And it's similar type things. I'll leave it like that. So the photon energy, if you remember, Planck's law, H times frequency, Planck's constant times the frequency, is equal to the difference between the high energy and low energy. In other words, when it gets up, and these are the Balmer lines calculated by Balmer, exactly those same things that you calculated, okay? And that's when they fall from level 6 to 2, 5 to 2, 4 to 2, and 3 to 2. Those are the ones you were punching in your calculator. Okay. So here's the quantum theory of the atom. Okay. Now, this is a really busy slide, and they don't go into great detail here. They measure the energy here in joules, okay, and you see how small that is. The energies are measured in electron volts, which is an interesting concept because what is a volt? A volt is the energy per unit charge. And the smallest unit charge you can have for charge is an electron charge. So electron charge times energy per unit charge would be an energy unit, and that's called electron volt. Now the interesting thing is they're all measured with negative numbers, okay? And as you're going increasing a negative number, you're getting more and more negative, so you're getting lower and lower energies, okay? So it's a little bizarre here, but it is true. Now this negative 13.6 they have down here is what they call the ground level, the minimum level you can ever reach. Most of the time we don't go down that low. So that's why it's always going to 2 here, and this is what's creating those spectra, okay? So the lowest energy level is called the ground state, way down there. That's the negative 13.6, okay? The higher energy levels there are called higher states or excited states. So all these are excited states here. They jump from one to another and give off radiation. The photon energy equals the difference in the state energy. So the photons given off, that thing of light giving off, is the difference here, and there's the red, the blue-green, the lower violet, and the upper violet, okay? The hydrogen atom is the example of the energy levels, the line spectra. So this was Bohr's model, and just like Balmer, it worked very nicely for hydrogen, the hydrogen alone. It didn't extend to helium or anything else. Things got so much more complicated so quickly. Okay? Now, this is what I just said. Bohr's theory only modeled the line spectrum of hydrogen, just like Balmer's theory, the equations only work for hydrogen. The Bohr's model theory only modeled the spectrum of hydrogen. Further experiments established wave-particle duality of light and matter. Oh my word, what does that mean? Okay? There was a guy named Young. I can't remember his first name. Let's see if I can find it here in the book. I don't know for sure that I can. Here he is again. Okay. I can't find, oh, no. I can't find Young's first name. It's probably in here somewhere, but I can't see it. But I just realized since I turned the page, I kind of blew something here. We had another example that I skipped over. So before we get to quantum mechanics, let's back up. And we'll use the same slide and clear this. And let's do example 8.4. An electron in a hydrogen atom jumps from the excited state level N4 to N2. What is the frequency of the emitted photon? I'm pretty sure we just did that. Well, we didn't do it this way, though. Let's do it this way. Okay? So what we're going to do is go back to this slide, and we're going an electron in a hydrogen atom jumps from excited energy level N equal 4. There we are right there. Let me get my pen back. n equal 4, okay, to n equal 2, okay? What is the frequency of the emitted photon? Okay? Okay? Here is your equation right here. So we're right on the right page here. We're looking for that frequency of the emitted photon. So what's your energy high? That would be the 4. And that's what confuses me here. It says it jumps from 4 to 2. Seems like to me that it should be falling from 4 to 2, but not jumping. But anyway, let's do the energy high, which is they want it in joules. Oh my goodness, here's Rhodesia. Hungry. All right. So the energy high in joules, we're going to use the joules here, is a minus 1.36 times 10 to the minus 19 minus the energy low, which is going to be the minus 5.44 times 10 to the minus 19. And these are in joules, by the way. Energies in joules. Okay? So if you got a calculator, you can do it on that. I think you can do it probably in your head almost. This is 5.44 and 1.36. You subtract that from there, you get 4.12. No. 0.8, I believe, times 10 to the minus 19. Let's see if I did that right. Yeah. Okay. So there's the difference. And take that number and divide it by H, which was, do they have H on here? I'll have to go back a slide or two. 6.63 times 10 to the minus 34. 6.63 times 10 to the minus 34 joule seconds. And this, remember, was joules, so the joules cancel out, and you'll be left with per second, which is going to be your frequency. So 4.08 times 10 to the minus 19 divided by 6.63 times 10 to the minus 34. And Kelvin's here. Anyone got a calculator?
So
What you get?
I got so 4.0. That's what we on.
Oh, okay. 4.08 EE or EXP minus 19. 4.08 EE or EXP minus 19 divided by 6.63 EE or EXP negative 34 equal.
63?
Whoa.
2.63, right?
6.63. Oh, I'm sorry. 6.63 EE or EXP negative 34.
5.9.
Okay, now that's not what they got. Okay, let's try it again. Let me make sure I did it right. Yeah, 4.08 EE or EXP negative 19 divided by
Close parentheses.
You don't need any parentheses. 6.63 EE or EXP negative 34 equal.
You divided, right?
Yeah, divided by. What you get?
5.9.
Okay.
I don't know what I need, because I said E into the negative 19.
Okay.
I'll start over quick.
Wait. Okay. You know, it's not.
It's the X to the negative 1 right
No,
here.
no, you don't need that at all. Okay. You look for your EE or EXP key, the one that you use for the scientific notation. There it is. No, this is EE. Second that. So
I did the wrong set.
Yeah.
I did the E's.
4.08.
4.08.
And then do the second EE. And then type in negative 19 divided by
6.63.
right, 6.63. E, yeah, negative 34. Okay.
And close enough?
No, I don't think that's right, but let me check. I didn't watch you do that last part. It should be 6.15. So let me slow down.
4.08.
Six point one five. There it is. And what's your exponent?
14.
Yeah, positive 14.
14.
6 point, what was it, 15?
15.
15 times 10 to the 14, and that's hertz. Per second is a hertz. That's the frequency of, I think that was the blue-green light.
Yes. Right.
Blue-green light and the hydrogen ion. Yeah. All right. So there was that one. All right. Now move back to quantum mechanics. This is 8.3. Okay. Bohr's theory only modeled the line spectra for hydrogen. The other things were far more complicated. Further experiments established, okay, and here's where we were before. Young, I can't remember his name. I sort of want to say Ernest, but it wasn't, I don't think that it was Ernest Rutherford. I can't remember his first name. But he did this two-slit experiment that produced interference patterns for both photons, which are energy packets, which we figured, yeah, that's going to go into waves, but also for electrons, which are particles. And that led to this concept that both waves and particles travel both as, okay, already we had that the light acted as a particle of light, the photon. But then we found that electrons acted like a wave of electrons. So particles or electrons acted like waves, and light, which you think of as waves, acted like particles. And that's what they call the wave-particle duality of light and matter. Now, it only works for tiny, tiny, tiny little matter pieces, like electrons. Okay? But it does work for both. Okay? And his two-slit experiment showed that for both photons and electrons. You had to be pretty careful how you produce that, but it did show it worked. Now, so here we have that electrons have to follow these wave patterns. And that's what we call matter waves. And there was, I'm pretty sure he was Italian. No, French. Yeah, French physicist Louis de Broglie. Now, when I took quantum mechanics in undergraduate in college, I had this Irish professor who had the strongest Irish brogue I've ever heard, and I could hardly understand half of his words. And when he said the Broglie, it came out rolling those R's, and it just sounded like he was harking up something really bad. But anyway, that was in 1903. So notice how fast things are happening here. He postulated these matter waves. Young has shown they do exist. He postulated how they could work in the atoms. The wavelength is related to the momentum of the particle. The matter waves in atoms are standing waves, which means they don't have discontinuities in them. Now, I don't know if any of you have asked this question before been to the McWane Science Center. Do you remember a display over on the side somewhere there that you could set up a vibration and you had it sort of in the dark, and then you had a strobe light flashing, and you put sprayed water droplets in there. You had an atomizer and did that, and you would see the wave patterns develop there. And when they were all chaotic, they weren't standing waves. But when they went through nodes, they were always moving, but they looked like they were just standing there. Okay? That's what we mean by standing wave. And the next figure is kind of going to show that. Well, no. Here's the Broglie's formula. That the wavelength is related to momentum, inversely related, and guess what constant shows up here as the constant of proportionality? Good old Planck's constant again. This was 23 years after he showed it for quantization of energy. Here it shows up again, and it makes perfect sense to be here, but now it's relating wavelength to momentum. Okay? Because these are particles, they have measurable mass, even though incredibly small, measurable velocities, probably incredibly fast, and it relates the wavelength to that momentum. Okay? Beautiful, simple little equation. And here's what the model is. Remember we said that the wavelength, the electrons are restricted to a given orbit. And we usually express that as a shell here. But actually they don't follow that shell. Here's what they do. They do a wave pattern on that shell. And for it to work, it has to be a standing wave. In other words, everything connected here and always connected. If you had something like this, it's not going to work. This is not a standing wave. This is a standing wave. So there's only certain frequencies and energies that make this work. Anything other than that, it all falls apart. And because it works, you know they have to be standing waves. Louis de Broglie came up with that concept. Okay? The matter waves. The matter waves are standing waves within an orbit. Okay? Now this led to another big scientist, and his name, and I'm jumping ahead, so let's go back. We'll do it right here. Do example 8.5 here. What is the wavelength associated with a baseball? Hey, that's not going to be very reasonable, is it? The wavelength associated with the 0.15 kilogram baseball. Let me see if I can get his formula. Yeah, here it is. I'm going to leave that up here. So what is the wavelength? So we're looking for wavelength, okay, associated with a 0.15 kilogram baseball. Well, this is going to be Planck's constant, 6.63 times 10 to the minus 34. I almost put 43. 34. Let me clean that up a little bit. Okay. Minus 34. If I can get my pen to work right. There we go. Joule second divided by the mass of, what did I say? 0.150 kilogram baseball times the velocity of 50 meters per second. Okay. Sorry. Okay. Now, we've got a little bit of fiddling around to do here. This is 6.63 times 10 to the minus 34. A joule is a kilogram meter squared per second squared second divided by, that's what a joule is, multiplied by second, divided by 0.150 kilogram and 50.0 meter per second. Okay, so let's see what's happening here. Obviously the kilograms can cancel out. One of these meters cancels out. Okay, this second here cancels one of the seconds out, and you're left with a per second here and a per second there. Those per seconds cancel out. So that leaves you just a single meter, and that's what your wavelength is going to be measured in meters. So this is a pretty, it's a reasonable calculation. The units work, so it's 6.63, your second EE, negative 34, divided by. Now, do you want to multiply these together, or you want to divide them separately?
I do it together.
Do it together. So if you do a divided by, then open parentheses, 0.150 times 50, close parentheses, then hit equal.
2.21.
Okay, let's see what they got. Say that one more time.
2.21.
No. Let's try it one more time. Okay. 6.63 EE or EXP. You got second EE. Yeah. Negative 34.
Right.
Divided by. Open parentheses. Okay. 0.15 times 50. Close parentheses equal.
8.84.
Ah, there we got it. And that's 8.84
times 10 to the negative 35.
10 to the negative 35, and that would be meters. That's a pretty small wavelength, an incredibly tiny wavelength. A millimeter would, in millimeters, that would be 8.84 times 10 to the minus 32 millimeters. So you are incredibly small. So you're not going to notice a wavelength with a baseball. Okay? But let's do something very similar and do it with, I hate to erase it all, but I think I will. What is the wavelength associated with an electron with a velocity of 6 times 10 to the positive 6 meters per second? So the wavelength would then be 6.63 times 10 to the minus 34, and a joule is a kilogram meter squared per second squared times second divided by, now we've got to get its mass. Now, I don't know if your book has it or not, but in my book the mass of a proton is in the front inside cover, and that's 9.11 times 10 to the minus 31 kilograms. So 9.11 times 10 to the minus 31 kilograms, an incredibly small mass, okay, times, and they gave you the velocity of 6.00 times 10 to the, I believe it was 6th, yeah, meters per second. Okay. Now, on your calculator, 6.63 second EE negative 34 divided by, open parentheses, okay, 9.11 second EE negative 31. Oh, okay, am I getting ahead? Oh, and here's Samaya. Let's see, did she make it in time for class? I mean, just barely, by the skin of her proverbial teeth. Okay. What's that? Okay, let's slow down. Let's back up. I'm sorry. I saw your question. Okay. 6.63, second EE, negative 34, divided by, open parentheses, 9.11, second EE, negative 31, times 6, second EE, 6 again, close parentheses, equal.
1.21.
Say it again?
1.21.
No. Wait. No, wait, I'm looking at, wait, you're probably right. I'm sorry, I was looking at the wrong answer. 1.21, is that what you said?
1.21.
1.21 times 10 to the minus 10. Meters, that's it. Now that's still an awfully small number, but it's certainly something we can measure.
Yes.
Okay. Now, oh goodness, did Wesley ever make it even more by the skin of his teeth? He made it here for break time. Wow, what a guy. Okay. Okay.
You're good.
Okay. We're not quite ready for break, are we? Don't we have a couple more minutes? Well, no, it's pretty good. Okay. That was example 8.6. Okay? All right. Let's see what the next slide was. Wave mechanics. Okay. So that's going to start the next section, and this probably is a good place for a break time. Okay? So just to rehash for everybody, you sure you can handle a break now, or you're not too tired? Okay. Okay. All right. What we've got here, we're going almost 4 hours today on the lecture, and so far we've made decent progress. We may or may not finish before 5:15, because that's when our test is. But if we don't finish, then we'll finish Chapter 8 on Tuesday, then have the lab on Chapter 8 on Tuesday.
And take a test on Tuesday.
If you want to, but I thought you said you'd rather wait till Thursday.
I'll take my final exam on Thursday.
Okay.
Well, I'm going to take the lab and the test on Tuesday.
Okay, now the final exam, realize is only going to last you about 15 minutes. You sure you wouldn't want to? Yeah. You sure you wouldn't want to do both tests on Thursday?
Yeah.
So we got a test today?
We have a test today on Chapter 6.
A test Tuesday?
Tuesday on Chapter 8, and then
Okay.
I'm going to wait for Thursday to take the final.
Okay. Okay, what I'm suggesting,
So just take both of the tests on Thursday.
either, yeah, I would suggest taking them both on. See, I had planned to give them both. Your final exam would be the Chapter 8 test and the comprehensive. And I think that would just make more sense. Okay. All right. But here's the thing, folks. The odds are you're going to have plenty of time Tuesday as well. So if you wanted to opt to take one or both tests on Tuesday, you have that option. But you will need to know by the end of the period today, so I'll know when to order the pizza, whether to do that on Tuesday or Thursday. Thursday? Okay. So what we'll do, let's pause here and take a quick break. Try to keep it 30 minutes. Sorry, I forgot to turn this back on. Okay, as soon as the projector comes up, while we're waiting, since a few people have come in kind of late, and you may not have heard everything, let's go over how things are panning out. We're working on Chapter 8 today, and we'll be working on it until 5:15. It's now almost 4. Okay, and Brandis is back. Okay? So, depends on how far we get. There's a real good chance we're not going to finish chapter 8 today. Well, we might. We'll just see. Okay? If we do finish chapter 8 today, we certainly are not going to have time for the lab, but we'll have the test for chapter 6 today. Okay? So that's going to wrap up today. Then Tuesday, we'll either finish 8, or if we finish it today, we'll have the lab on 8. But nevertheless, we'll have the lab on 8 on Tuesday. It's not going to take us long. I'll allow at least 2 hours for the lab. If we have to finish a chapter, it'll be a little more time. And then after that, it depends on what you want to do. If you want to go on and work up a formula equation sheet and have the test, you can. I would have planned to have the test on Thursday, but I'll try to have it ready on Tuesday if someone elects for that. And once you finish the test for 8, if you elect for it and want to do it, you can do your final that same day too. But you don't have to. That's scheduled for Thursday. But if it's beneficial for you to take it earlier, you can, but I don't want to push you that way. I'm going to be here both days, so it's not going to make a bit of difference to me. Now, let me also ask this. Are any of you graduating this term? Not. Okay, that's good. Because if you were graduating this term, I have to have your grades in by Friday noon. So I'd have to have everything done Thursday. But as it is, you've got plenty of time. Okay? The rest of you, your grades are going to be due in by noon on the following Wednesday. But don't sweat. Hopefully they'll be in way before that. Now let me also tell you this, in case this is new to some of you. Normally you might check your grades on Student Suite. Don't do it during Finals Week. You probably won't be able to log on because we only have, this is an ancient system and there's only so many portals, something like 16 or maybe even 32, but every student can't be on it looking, otherwise instructors can't put the grades in. Okay, so look for your grade on Blackboard. Once we put it in Blackboard, then we'll put it in Student Suite. Or we'll put it on the suite, it's Faculty Suite for us. And then you'll be able to see it after Finals Week are over. But you'll see it first on Blackboard. Okay. Any questions? All right, let's get back to where we were, and this is on page 216, wave mechanics. All right. Erwin Schrödinger, an Austrian physicist. Now notice here, Europe, the U.S., all of us are involved with this development of quantum mechanics. It was probably one of the best examples of the coming together internationally to develop a theory. And these guys worked together and fed off each other. It was really an incredible bunch of people. And Grayson is here today. Okay. Okay. So here we have Erwin Schrödinger. He developed the concept and started the process of what we call wave mechanics. It's part of quantum mechanics, but remember we've got now the even matter electrons travel in a wave-type pattern. De Broglie found out they had to be standing waves. So here's what Schrödinger did. He treated the atoms as three-dimensional systems of waves. Sort of a new way of looking at it. Okay? It contains successful ideas of the Bohr model, but remember the Bohr model only worked for hydrogen. It didn't work for the more complicated atoms. But it did much, much more than just containing those ideas. It described hydrogen atoms really well, plus many electron atoms. So it now is the standard. It forms our fundamental understanding of chemistry. Now, if you would have asked me, I would have said it's a physics model. And that's what it seems like to me, but this helps explain what goes on in chemistry as well. Okay? Now, here is basically that quantum mechanics model. Now, this might sound, I don't want to say confusing, but at least slightly complicated, just because it has so many different numbers. but the numbers are related. The quantum numbers specify electronic quantum states. Think energy levels. Okay, that's what these numbers are doing for us. Here's sort of the visualization. The wave functions, picture those as probability distributions. Now, there is the probability distribution of a single electron. It could be anywhere there, okay? Well, that's pretty broad, okay, and it's really scattered, and you have a lot of variation. But if you take out 10% of that, now you've got a much cleaner model. That's your 90% probability volume. Now, it really gets to me, because I'm more used to in science thinking of things with definite answers, not probable answers. And this is where quantum mechanics really gets fishy, okay? So you're thinking in terms of these probability distributions. The electrons are not necessarily any one place. They are delocalized. You can't say, oh, there's the electron, okay? It's somewhere in this range, okay? Now, here are these electron quantum numbers in the atoms, okay? And it may sound confusing, but it really makes things much simpler. The first of these is what we call the principal quantum number, N, okay? Now, it's a number, but they give it a symbol for a letter N. Think of that as an energy level, okay? And that basically is the average distance from the nuclei. Now, that's an average distance, which does leave a little bit of wiggle room, and I'll explain that in a minute. Because if you look at this, the average distance would probably be somewhere around in here, okay? Because it could be way out there, even way out here, but its average distance would be somewhere around there. You have more of them concentrated here, so these don't contribute as much to the average, okay? So that's your principal quantum number, N, okay? We're going to come back to N a little bit later. Then we have what they call the angular momentum quantum number, L. Okay? N for number, that sort of makes sense. Angular momentum quantum number, L. I don't know where the L came from. There is an L in angular, but that's a real stretch. Now what this is describing, is a spatial distribution. This is average distance from nucleus. This is a spatial distribution. Okay? Now, the angular quantum number L is labeled with letters, not numbers. Okay? The principal quantum number N is energy level. 1, 2, 3, 4, 5, 6, 7. That's as high up as we ever go. The angular momentum quantum number is specified, labeled with letters. S, P, D, F. Technically, there's G and H, but we've never reached there. So don't worry about that. S, P, D, and F. Now, I don't know where they came up with those either. S, P, and D seem to have nothing to do with each other, even F. After that, G, H, I, J, but we never go there. Okay, so just remember, S, P, D, and F. Okay? Now, the third, the magnetic quantum number. It's a spatial orientation of the orbit. Now, this is a spatial distribution. This is a spatial orientation of the orbit. Okay? Now, not very clear to me, but anyone else, I think at this point, what that means. Not as labeled with anything. It doesn't have a thing. You would think maybe it was M or something. Nothing. But then we have the spin quantum number. And this is the electron spin orientation. And I'll tell you what this one is. It's real easy. Up or down. Positive 1/2, minus 1/2. That's all there is to the last one. Okay? The third one, pretty foggy right now. But let's see how these come together. All right. Your energy level in 1, 2, 3, 4, 5, 6, 7. That's as high as we go for that. Okay? Spatial distribution. Your s orbital, and sometimes called a suborbital, is basically like this. Your p orbital would be like this. So you see that's the spatial distribution. Your s orbital is basically centered around the center, basically, and could be anywhere in there, mostly toward the inside. Your p orbital are done in lobes, okay? You have one set of lobes there, one set here, and one set there. That's what the spatial orientation is. I just gave it away. S orbital has only one spatial orientation, just around the center. The p orbital has three. One along, say, the x-axis, one along the y-axis, and one along the z-axis. So you see there isn't really a number there or a letter there. It's just describing how those distributions are spaced. Oh, goodness. Even Austin's here today. Okay. Good deal. And to your joy, I'm sure, you get to hear a lecture. Okay? We'll still be talking for another hour plus. Okay? And then we're going to have a test on Chapter 6. Okay. Okay. So coming right in the middle of quantum mechanics. Yay. So there's S and P. All right. There are three p orbitals. The SPD, the spatial distribution, that's the angular quantum mechanic numbers. How they're oriented, that's the magnetic quantum number. So you see there's not anything you really do with this. Here is one along the x-axis. Yeah. One along the y-axis. I don't know why they put y like that. And one along the z-axis. And they call this px, this one py, this one pz. That should put this over here. Okay. Strange the way they placed it here. Those are the easy ones to do. We've still got D and F to go. Those are really going to get complicated. Oh, they're not going to show it here. Oh, my goodness. They keep coming. Michaela's here. And Zaria's here. Anyone else come in such a call? We may actually have a quorum. Okay. So that's what our third quantum number was, magnetic quantum number, how the orientation goes. Okay? Now I'm going to give you a hint here. S has one orientation, one only. P has three. D has 5. And F has 7. Notice they're odd numbers. Okay? Those are odd numbers. So that means there are one orientation for S, 3 orientations for P, 5 orientations somehow for the D, and 7, I don't even know how you can picture that, for the F. Okay? Since they didn't show it on the slide, let me do this. Now, I'm going to pause for just a second here. More than a second, probably. There is a Science and Society at the top of the page on, it says atomic research. Okay? 2 types of scientific research, basic and applied. Basically, the basic research is just going after the big concepts, like setting up the quantum nut, Schrodinger's equation, that kind of stuff. That is basic to come up with that. Then the applied is how we use that, how we can take advantage of it, what predictions we can make. Both of them are very, very important. Some of them more esoteric than others. Like the basic, you might not see where you're heading, but hopefully you'll see that. Okay, and then, so let me show you like I showed you, one and only one S orientation. That's just around the center. This shows the 3 on one graph rather than 3 different ones. There's along the x-axis, that load, along the y-axis, z-axis. 3 different orientations for the P. This is the 5 different orientations for the d orbitals. And I can't even begin to point those out, okay? But there's 5 of them there. And how in the world, so each of 5 sets of loads holding 2 electrons each for a total of 10 electrons, okay? So that's your D. F7, oh my word. I don't even see how you could fit that in there, but somehow they do, okay? What mind came up with this, I don't know. Schrodinger is weird. But the spin quantum number, spin up, spin down, easy, easy, easy. Okay. Now, this is leading to the table on the top of page 218. They don't show it in the slide set. Oh no, here it is in the slide set. It's shown after the spin, but here it is. Now, hopefully this will start tying together a little better now. When you're on that first energy level, n equal 1, you only have one sublevel, S. This is angular quantum mechanic number, not a number, it's a letter, S. Okay? Now that S sublevel can only have 2 electrons. One spin up, one spin down. Okay? So the maximum number of electrons in the first level is 2. That means the maximum number of atoms and elements in the first level is 2. Okay? Then when you go to n equal 2, you have an S sublevel, that's your angular momentum quantum number. Now you can add a P. Remember though, S is one and only one spatial distribution, and it can have 2 electrons, so there's 2 electrons in S. The P, however, can have 3 different orientations, so that leads to 6 electrons, 2 per level, 1 up, 1 down. So you can have in level 2 only 8 more electrons, only 8 more protons, which means only 8 more elements in n equal 2. But you can't have 8 there. N equal 3, you can have an S with 2, just like before, only 1 orientation, 2 electrons, 1 spin up and 1 spin down. P has 3 orientations, but each orientation can have 2 electrons, 1 up and 1 down, so that has your 6 electrons. You can have a D in n equal 3. I'll tell you right now, we don't yet. We will later, but we don't yet. You probably don't know what I mean. Remember, D can be up to 5. Well, it has 5, and each one can have 5 distributions. Each one can have 2, so you can add 10 more electrons. So you can have up to 18 in level 3. Okay? Because you just added 10 more to the 8 that you had now. You still have 2 there, 8 more here, 18 more here. When n equal 4, now you can add another. You have your S with 2, your P with 6, your D with 10. F, remember, is 7 orientations. Each one can hold 2. Now you're 32 more. Okay, now if you add these up, this is only going up to n equal 4. Okay? This would be 50, and 10, that's 60. That gets you more than halfway down the periodic table. Periodic table shows up to 118, so you're halfway there. When you add n equal 5, that increases yet some more. N equals 6, even more. N equals 7, that's as high as our periodic table goes. Whether somewhere in the universe there's some with greater than 7, I don't know. But that's as many as we have. Okay? And we don't fill up all these either. Okay. So, let's look at our electron configuration. This is topic 8.4. By the way, I think I'll go on and do this. No, I'll wait till then. Okay. the arrangements of electrons into atomic orbitals. We start filling one at a time. Okay? And every time we add an electron, that means you added another proton, so you're a different element. So we start with principal, which is N, angular momentum, that's L, magnetic quantum number, that's how you orient your L, okay? And then your, they specify an orbital. And then up or down is your last bit. That's the spin quantum number, okay? These specify the atom's quantum state. Along came, I'm pretty sure he was Italian, Pauli. Let me see if I can confirm that. Yeah, here we go. Nope, Austrian, another Austrian. Wolfgang Pauli, okay? He came up with this principle called the Pauli exclusion principle. He said that each electron has a unique set of quantum numbers. So if n's equal to 1, then L could be S only, okay? And then you could only have two electrons there, one spin up and one spin down. So 1, S, 1, and 2. That's 2 electrons. The next level, n equal 2, you could have an S with an up or down, and then you could have P with an up or down, 1, 3 different P's. So each one only has a unique set of quantum numbers. The maximum of 2 electrons per orbital, and that's one would spin up and one would spin down. That last the spinning quantum number. The chemical properties are determined by these electronic structures. So that's why they say Schrodinger's wave equation gave the basis for the principles of chemistry. We knew the principles of chemistry long before we knew Schrodinger's wave equation, but Schrodinger's wave equation explained why they have these principles. Okay? Now, okay, I'll wait one more minute to do that. How do we write these electron configurations? Okay? The electrons fill available orbitals in order of increasing energy. Now, here's the sort of surprising part. Energy level 1, okay, it's always less than any of the others. 2 is always less than any of the others. 3, 3s, and 3p are less. 4s is next. 4p is next. And let's see, you keep on going. But after a while, then you jump and go back to 3D. Okay, 3-dimensional. So there are some unusual things about how they fill. Just because it's energy level 3 doesn't mean always 3 is less than 4. There are some 3s that are greater than, like 3D is greater than 4S. But we'll get to that later. So here are the capacities. When you have an S, only 2. Remember, S only has 1 orientation, only can allow 2 electrons, 1 up, 1 down. P has 3 orientations, so it's allowed 2 electrons per orientation, so that's 6. D has 5 orientations, so it's allowed 2 electrons per orientation, 1 up, 1 down, so it's up to 10. And F has 7 orientations, so it's up to 2 electrons per orientation, so you can go up to 14. So here we're going to do strontium. That's 38 electrons. Now, how do you know that? Okay? Here's how you know it. Go to your periodic table. We're going to do this next. I've been itching to get there. You've got to find strontium. There it is, right there. Okay? And what's strontium? Number 38. The atomic number of strontium is 38. What does that mean? 38 protons, exactly. Okay? And if it's a neutral atom, that means 38 electrons. To be neutral, it has to have the same number of electrons as protons. Now, while we're here, if you look down at the atomic mass, it's just about 88. Okay, it's 87.62, so we'll go around that 88. You subtract 38 from 88, and you find it has 50 neutrons. But neutrons don't have any charge. You can have as many or a few of those as you want within certain limits. So the rest of those are neutrons. They don't contribute anything charge-wise. So you got atomic number 38, meaning 38 electrons. So let's start filling that. Well, in the 1s, you can have 1 or 2. So you have 2 electrons in that first one. Then 2 has an s, 1 or 2, so that gives you up to 4 electrons. But then you have 2p, which is 6 more. That gets you to 10 electrons. Then you go down to 3. You don't go to D yet. 3, 2, so that gets you up to 12. 3p, 6 more, that's 18. But then you go to 4, okay? And here's how this works, okay? You list them, 1, 2, 3, 4, 5, 6, 7. Remember, we only go to 7, okay? You have your S's always, then your P's, but you don't have a P for 1. It only has S. 2 only has S and P. 3 has S, P, and D. 4 has S, P, D, and F. You don't ever go past F. 5 then would only have S through F. 6 only S through F. If you had G's, they'd be over here starting here, but we don't ever get that far, okay? And 7 would have D, would have F, would have G, but we don't ever get that far. Now, this is a weird looking diagram because of the arrows. And here's what the arrows mean. Okay? They do it in the book. They don't do it on the slide set. They'll try to do it like they do in the book. You start here at the end. And maybe I'll stay. I'm starting to change color. But maybe it's good to stay in red. So you fill up 1, 2 electrons here. Then you go back to the top. Then you do 2 more electrons here. And back to the top. So you're up to 4 electrons now. Then you do 2p. That's 6, remember? So that gives you 10. And then these 2 make it 12. And then you go back to the top. Okay? And then you do 3p, which again is 6. So that gets you up to 18. 4s. So you don't do 3p, 3d. You do the 4s before you do 3d. This is actually a lower energy level than that, okay? Even though we call it the principal quantum number 4, it's actually lower energy than 3D. So I can't remember what we're up to. 2, 4, 10, 12, 18. That's what we're up to. 18 and 2 is 20. Go back to the top. And now D, remember, was 10. So that gets you up to 30. 6 more is 36, and 2 more are 38. Stop right there. You filled strontium. See how that works? Okay. So use this diagram, and this is how you fill your electron shells. Now, and here's how you write it. 1s2, you have 2 electrons there. 2s2, 2 electrons there. 2p6, remember you can do 6 electrons there. 3s2, that's 2 electrons. Go back up to 3p6, 4s2, 3d10, 4p6, 5s2. When you add up to 38, you stop. You're at strontium. Okay. Now, okay. I can't wait any longer. I want to show you this. What we've just described is right here in the periodic table. Remember the first energy, N equal 1, that's your period. You get hydrogen, helium, S1, 2. 1 electron for hydrogen, 1 proton for hydrogen. 2 electrons for helium, 2 protons for helium. You're through with the first row. Then you go to the second row. N equal 2, S2, there's your 2 for S. Lithium, beryllium. And then you go to your P. 2P is boron, carbon, nitrogen, oxygen, fluorine. There's your 6 right there. 1, 2, 3, 4, 5, 6. Then you go to 3S. See, that's next. And you do sodium and magnesium. 2. Okay? Then you go up to 3P. Okay? And 3P is aluminum. There's the first one. Then there's your 6 3Ps. And then you come down to 4S. There's your 2 4S. And then you see at 4S, you go back and fill in 3D. And that's where these start here. How many were those? 10. Remember, 1, 3, 5, double 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are the 10 elements that are now filling the 3D shells. Higher energy than 4S, believe it or not, but they are. So these are 3D shells here. Then you go and fill your 4Ps, and there's those 6 there. Then you go down and fill your 5 S's, and when you fill that second one, there you are at strontium, right there. So the quantum numbers tell you exactly how these fill up. The interesting thing is, Mendeleev had this developed before he knew why. Schrodinger's wave equation explained why, using these quantum numbers and these principles of the quantum numbers. So that's the connection between quantum mechanics and what we already knew was the periodic table. It fits hand in glove. To me, rather amazing. Okay? So that's what we're talking about here. The periodic chemical properties are based on these quantum numbers we just described. Okay? These are understood in terms of electron configurations. How are these electrons configured? Why do they act the way they do? Well, this is it. The electrons in the outermost orbits determine the chemical properties. Okay? And this is summarized in the periodic table. Okay? Now, what I just described to you as we were filling that periodic table, when you're over here in this first column, see the periods where you're in quantum numbers, 1, 2, 3, 4, up to 7. Okay? Your columns here, they tell you more. Okay, the rows are your periods. Okay? I realize it was there. The columns are the families or groups. If you're here in the first column, now hydrogen is a little strange, but it fits here. Then lithium and all these others, they are much more like each other than the things in the rows. They're very similar in the column. Why? They all have a 1s or a s1 electron. And those s1 electrons are out there all by themselves. So they're easy to lose. So these form strong electromagnetic bonds. Okay, I'm going blank on what you call it. Where they gain electrons, these lose electrons and become a positive positive ion, and whatever they lose it to, that becomes a negative ion, and then it's an ionic bond. That's what I'm trying to think of, ionic bond. And quite often they are lost to your column 7 because they have all the electrons except 1. If they had 1 more, they'd be happy campers. So they steal it from the column 1. Okay, now they have 8 in their outer shell. They're just as happy as these. So let's, let me explain. So this first row, the first column here is called your alkaline metals. Even though hydrogen obviously is not a metal. Okay, lithium's a very soft metal. Sodium's pretty soft. Potassium's getting a little harder and they get gone. Okay, that is the alkaline metals. Alkali metals. Column 2A is your alkaline earth. You can put in metals too, but they just call it alkaline earth. Beryllium, magnesium, calcium, blah, blah, blah. Over here in column 7, those, I can't hold this much longer, is halogens, column 7A. They like to steal electrons because they're 1 electron short from having a filled shell. Okay? They want to have a filled shell, so those they steal and become negative ions. These become positive ions, those become negative. These become +2 ions. These sometimes become -2 ions. Okay, so now I wanted to get to the noble gases. Now, why do they call them noble? They're not princely or anything. Why they call them noble is they're content. They have everything they need. They don't combine with anything. Just like nobility sticks up their nose and they don't marry commoners, right? They don't combine with anything else. Because guess what? Helium, the S2 is filled. What's it going to combine with? Nothing. Helium gas doesn't combine with anything. Argon, or neon doesn't. Argon doesn't. Xenon doesn't. Krypton doesn't. Xenon doesn't. And radon doesn't. They don't combine with anything else. They are the noble gases. There's one more there they don't have a name for yet. Okay. We may not have even discovered it yet. Those are your noble gases. They have filled shells. They don't combine with anything. And that's why they went from making blimps out of hydrogen, which would explode like crazy, to filling them with helium. Not quite as light a gas, but wouldn't combine. It would not explode and combine with anything. Neon and neon lights, they don't combine with anything else, but they can send off some really incredible light. Argon, you know your incandescent light bulbs? If they had any oxygen in there at all, those titanium filaments would burn up immediately. That's why if you ever puncture a light bulb with a pin, say, don't try this at home, Mom and Dad will be mad at you. It'll immediately blow because the titanium gets so hot, it will oxidize and blow in no time. So they fill those with argon gas. They don't combine, it doesn't combine with anything. Thermal panes on your windows. Sometimes they will pump argon gas into those so they won't combine. They're not supposed to fog up or anything else. They won't combine with anything. So, and the others get more rare as you go up. You have to get the Superman to get krypton. No, I'm just kidding. Okay. Now, the A group families are the main groups or representative elements. Those are the 1A, 2A, and then 3A, 4A, 5A, 6A, 7. In other words, those are the S's and the B's. Okay? The B group, if you look down here, they then become your transition metals. And those are when you're filling the D suborbitals. Okay? S, P, D. Remember, we did get the F's. Here are the F's down here. 7 times 2 is 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So everything goes. They really fit in right here, but if you put them in there, the table would be like this long and have very little in them. So they put these down at the bottom, but they go right there. This one goes right up there. This one goes right there. And by the time you get there, that's why I say we don't ever go past 7. We haven't even filled all of 7 yet, okay? And we don't go past F. We don't have any G's because the energy structure that we showed back here, you would have to go here, here, and you still would be here before you ever got to the G here. No, the G would be right here. We don't fill that. We run out of elements before we get there. Okay? So we don't ever get to the next one, the G. All right, does that kind of make sense? So those are our shell capacities. You see it right there in the periodic table. 2, 6, 10, 14. Right there in the periodic table. Okay. All right, the B group are the transition. I already put it down. Transition elements here. Okay. Now, the ones down there at the bottom are called the rare earths. You don't find them frequently, and by the way, that's where uranium is, and that's where plutonium is. That's where a lot of your really dangerous nuclear chemicals are. So, I don't have to hold it up anymore. Here's your periodic table. Okay? 1A, alkali metals. Okay, soft metals. Here, alkaline earths, 2A. These tend to lose electrons easily. becoming positive ions. 7A is halogens, and these are your almost filled shells. This 8 is filled, almost filled, so they rip off electrons, okay, from wherever they can get them, and these become negative ions. And then you have, like, sodium chloride, salt, sodium iodide, potassium chloride, potassium fluoride. They really form strong ionic bonds. The ions, because of the opposite charges, they stick to each other like crazy, okay? Then you have your transition metals here. These are our common metals. Now aluminum is here, okay, and these are weak metals, but carbon is a non-metal, but it's still a pretty good conductor. But most of your conductors, there's your copper here, your silver down here. These are two great conductors, and gold is a great conductor. Look at that. 1Bs, good conductors. Why? Because they've got one electron that's free to move. Well, more than one, but those are your three best conductors right there. Silver, copper, and gold. Okay. Aluminum's next. Okay. Here's your three magnetic ones: iron, nickel, and cobalt. There they are, and they're all under what they call 8B. They all go together. These aren't magnetic, but those three are. Pretty incredible how many of your chemical principles are tied to these quantum numbers, because this table is put together according to quantum numbers. Okay? So let's look then at this. Your noble gases, filled shells, those are the column 8. There they are. Filled shells, they don't combine with anything. That's why they say they're inert. They do not combine chemically with anything else. When you have 1, 2, or 3 outer electrons, that would be in this, or that sometimes, okay? And then you get around to these 1Bs. These are the transition, but they still sort of act like they have 1 or 2 here, and sometimes 3 here, but they don't do it as strongly. But these are your ones that they tend to lose electrons and become positive ions. These are mostly your metals. That losing electron, that allows them to conduct electricity and heat really well, okay? When you have 5 to 7 outer electrons, that's in this range, 5, 6, and 7, they tend to gain electrons. Now, these will sort of do it too. Now, you can't really tie these in too much. I did a little bit, but those are the ones we're talking about, the A ones there. Those tend to gain electrons. These are mostly and they form negative ions. These are nonmetals, okay? Now, what do we mean by nonmetals? This is certainly not a metal. Carbon, that's like soot in your chimney, or diamond, those are not metals. Nitrogen gas, most of the gas in this room is nitrogen. Oxygen, next most is oxygen. Fluorine's a gas. Chlorine's a gas. Bromine, I think, is sort of a liquid gassy type thing. Iodine, but these are nonmetals for sure. Sulfur's a nonmetal. Potassium's a nonmetal. Silicon is a nonmetal, okay? So, those are your ones. Notice the stair-step pattern there. Those, the ones I just mentioned are nonmetals. Semiconductors are intermediate between the metals and the nonmetals. Here they are. These form most of your Silicon Valley, semiconductor, right there. Germanium, I think it is. I can't remember all the names. This is tin, this is another one, antimony, I think. But these form your semiconductors. They're not as good as metals, but they're not as bad as your nonmetals. They're your semiconductors. And that's where a lot of the industry, they do a lot of research with those, seeing what they can get. They have to be stable and they have to do their job well. So those are your semiconductors, intermediate between the metals and the nonmetals. And this is, oh, boy, strange place to put this one. Let me go back to my book. I've lost my place. Yeah. by the way, we're over here and they didn't quite mention this, but let me hit it now. Table 8.4 is your 1A alkali metal family, and 8.5 is your electron structures, your noble gases. We sort of hit on them, but didn't do. Periodic practice, there's a little something. We'll be doing that in your lab next time. Oh my, we're getting, no we aren't. We still got 30 minutes. So we're now into 8.6, metals, nonmetals, and semiconductors. Okay? And this is where this is what we call our electron dot notation. What this represents are the electrons in the outermost shell. Remember, your first column has one electron, 1s1 in the outer, 1s1, 2s1, 3s1, 4s1, 5s1, 6s1, 7s1. These have one electron in the outer shell. Really easy to lose them. The 2s, the s2, beryllium, magnesium, calcium, strontium, barium, and radium, these have two electrons in the outer shell. They're not as easy to lose as these, but they do tend to lose, especially these at the top. Okay? And then forget about the transition metals. Leave those out, all those D's that are in there. Let's jump to the A side, and these are your P's. Okay? Boron 3, carbon 4. Now that's exactly half filled or half empty. We don't know which. Okay? Sometimes they'll fill, sometimes they'll go either way. These tend to become positive ions more likely, especially aluminum, gallium to some extent. But now you're getting into the semiconductors here, so don't worry with those too much. But these tend to grab electrons because they almost have filled shells. This one's only missing one. These have filled shells. Now the first shell only has 2 electrons in it. That's a filled shell. The last one, these others have 8 in the filled shell. 2 plus 6 is 8. Okay? And those don't combine with anything, noble gases. These like to grab electrons and become negative ions. These lose and become positive ions. These do to some extent, just like these do to some extent, grab electrons. But you see, the more you get away from the ends here, they then, rather than stealing electrons or losing electrons, they share electrons. And oxygen, potassium, carbon, silica, sulfur, they all tend to share electrons more than gain or lose them. Because that's just way too many electrons to gain or lose. But that's what the electron dot structure means for you. The outer orbital electrons. Okay? Especially of your S and P's. The D's don't fit that as well. Okay. Now before we get too far here, in your text on page 222, there's a really nice blurb on rare earths. These are rare materials. That's why they get the name rare. They usually come in solids, so they're earth materials. And those are those 2 groups that are at the bottom that are filling those F sublevels. Remember? There's 2 at the bottom. 14 across the bottom there. Okay? Today, those not metallic elements are known to be more abundant in the earth than gold, silver, mercury, and tungsten. But the rarest of the rare earths, thulium, is twice as abundant as silver. So they have some rather strange names there. But frankly, what you'll find with those is they are useful in all sorts of advanced technology. Things like solar cells and things, they have found uses for these. Now here's an interesting thing. Where most of these rare earths are found, and this is sort of sad too, are in some of the less developed countries on the planet. I'm thinking the Congo, Democratic Republic of Congo, which I think is having almost a civil war now. They are so rich in minerals. Not just these minerals, lots of minerals. But yet their infrastructure is such that largely from colonialization days, they're just wrecked as countries. And these other countries, especially China, loves to go in there and exploit their materials. Yeah. So it's really a sad situation. Earlier, Belgium did it to the Congo. That used to be called Belgium Congo. They were just awful colonizers. Awful. Okay. Now, moving on the top of page 223, Mendeleev, Dmitry Ivanovich Mendeleev, a Russian chemist who developed the first workable periodic table. He had done most of what we see here. He had some blanks in it because there weren't metals to fill them up or elements to fill them up yet, but he predicted they would be there just based on the chemical activity. Long before Schrodinger developed, the wave mechanics, he had already done this. He knew what belonged there, but wow. Excellent paper topic if you haven't chosen one. And then there's a blurb at the top of page 224 on semiconductors, which is things like LEDs. Resources come from that. So a lot of good stuff there. All right. So let me go to, finally we hit the slide that shows this part, the semiconductor. So here are your metals. Strangely, they put hydrogen in the metal. It really is a gas, okay? It's a non-metal. But you see that first row is just too light. But everything from there on down, these are your metals, okay? Your non-metals are over here, including the noble gases. Those are non-metals as well. And then these along the border, above or below that jagged line there, those are your semiconductors. Now, I've heard gallium sometimes referred to as a semiconductor, but more germanium. So yeah, these are in here. Some of these real heavy ones are not, but the others are. So those are your semiconductors. I point these out because the lab you'll be doing on Tuesday is going to use a lot of this stuff we're talking about right here. You're going to have your book. You're going to do a paper lab based on that. Okay? And that, folks, is the last slide. There's some more stuff in the text. There's metals and charges. That's really a good read there. We've been talking about it for several chapters, but this is those free electrons. Those are free to move. That's why they're great conductors of heat and great conductors of electricity, because of those free electrons. Okay? The outer orbitals, they mentioned some things there. That's well worth a read. Now, we did finish the chapter, so let's do a quick review on what's going to happen next. We don't have time for the lab on this chapter today. Don't have time for it. Okay? But it looks like we may have time for the test from chapter 6. Shucks, you may get out early today. Wow. That's terrible. Cheating you out of your tuition dollars, I feel awful. I really do. Okay. Now, so what we're going to do, that means Tuesday, all we've got left to do is the lab for chapter 8. And if that's all you want to do, we can do that Tuesday. Now, for those who want to, we can have our test on 8 because we finished chapter 8 today. So we'll have our test on 8 on Tuesday, for sure. Okay? So the lab on 8, test on 8. Now you can stop there, go home early if you want to. And then come back on Thursday and do the final exam. But since you're going to have plenty of time, you can do your final, if you want to, on Tuesday. Do any of you have a feeling of whether you want to do that or not? Most of you? You don't have to. I'll be here Thursday, and you can take your test. But since most of you want to finish on Tuesday, want to go on and have the pizza on Tuesday as well. Yay or nay?
Yes.
Okay. Well, if we do any of you have any restrictions on dietary or other things that you either don't want pork or you can't eat? Pepperoni. I heard one pepperoni. Anything else? I'm getting
I don't eat
Little
ham.
Caesar because it's close. Say again?
I don't eat ham.
You don't eat ham. Okay.
Or sausage.
So pepperoni will be fine. Anyone prefer cheese? No. So you want me to get all pepperonis? How many pieces you think we need? We have a total of 18 people, I think. How many do you think that would be? About what?
3.
3?
Yeah.
Is that going to be enough for you guys? 3 pepperoni pizzas?
That's enough.
4? What you think?
I guess 4.
4?
5.
5? It keeps going up. How many? What you want? 5? 5 pepperonis? Okay, 5 pepperoni pizzas going for 5. That'll be Tuesday.
Yeah, Tuesday.
So when you come in Tuesday, the pizza will be here hopefully, or if not, it'll be here soon. Or to Austin. They'll all be gone before you get here. No, okay, I'm just kidding. Okay, I don't think 5 pizzas will be gone. If so, I'm amazed. Okay, 5 pizzas will be here as soon as close to 1:15 as possible. And what we'll do while y'all are eating your pizzas, I'm going to be returning all your labs and all your tests. Okay, that means I have to have them in before 1:15 on Tuesday, right? Okay, all your labs, all your tests. Okay, that's one. Then we'll do, once you've eaten your pizza, I've returned the labs, then we'll start on the lab for Chapter 8. When we finish the lab for Chapter 8, we'll start on the test for 8. Okay? That will be for everybody. Now, if some of you elect to do the test on 8 on Thursday, you can do that. But scheduled will be that. Then you can either leave or you can stay and do your final. That's up to you. I will be here on Thursday for anyone who wants to take the final on Thursday. Okay? And then on Thursday will be it. Now, since I got more people here than I did earlier, has everyone done the student course evaluations? Okay, if you haven't, please do those before the end of the term. Okay? Any questions then? Okay, now some people were talking about making up some tests. I think you will have time today. You'll definitely have some time on Tuesday, but let's see about today. So let's do today's test. Somewhere here, I once upon a time, oh, here it is. Had it. Okay. This is the Chapter 8 test. Is there any reason you want this left on any longer? Okay, I'm going to shut down the recording.